Manpreet, are you there?
Yes, sir.
Dr. Pant? Pradeep, sir?
Yes, sir.
Okay, Manpreet, let me talk to Dr. Pradeep. Dr. Pradeep, are you there?
Hello.
Hello, good morning, sir.
Good morning. Hello.
So, very good morning, sir.
Hello.
Yes, sir.
Good morning. Yes.
So, a very good morning to all the participants. Our today's speaker, Dr. Pradeep Chandra Pant, is among us. So, sir, I welcome you, and I am very much thankful from the behalf of Department of Physics and organizing committee of this short-term course on advanced energy material. So, thank you, sir. Thank you very much to spare some time and accept our request to be the part of this short-term course. So, Dr. Pradeep Chandrapant has vast experience in the field of renewable energy, more than 35 years. So, I am sure that we will have a great session in the morning. So, sir, now I request Manpreet to please chair the session or introduce our birthday speaker. Manpreet, please.
Thank you, sir. A very warm and healthy morning to each and everyone present here and on YouTube. I, Manpreet, on behalf of the organizing committee, welcome you all on the last day of short-term course on advanced energy materials. After the interesting talks on renewable energy, lithium batteries, multiferroics, piezoelectric, magnetoelectric, and thermoelectric materials, I'm sure you all will be very much excited about today's talk. Today we have with us Professor Pradeep Chandra Pant from the Ministry of New and Renewable Energy, New Delhi. Sir, it's a great honor to introduce you. Professor Pant is former advisor and scientist G in the Ministry of New and Renewable Energy, Government of India. He has received his PhD degree from CCS University, Meerut. His area of interest includes renewable energy technologies, energy engineering, energy economics, power generation, and photovoltaics. Professor Pant is an energetic professional with more than 35 years of experience in research and development, project planning and implementation, policy formulation, and education and training. Before starting his career as a scientist in the Ministry of New and Renewable Energy, he has worked as a project officer in Non-Conventional Energy Development Agency, Lucknow, Uttar Pradesh. He has conceptualized, designed, and developed state-of-art battery research and testing facility, solar energy training lab, SPV System Design Lab at SEC. He has represented ministry in several committees. He is also a member of ET11 and ET52 committees of BIS India for the development of standards on batteries and energy storage. I am very grateful that Professor Pant is here with us. I extend a very warm welcome to you, sir, and I request you to please enlighten us with your talk. Sir, please.
Thank you, Manpreet, for the kind words, and at least you have designated me as professor, which in any case I am not. But anyway, thank you for this, and good morning to all the participants. As Manpreet has told that I had worked in Ministry of New and Renewable Energy, so practically we are, or we were basically the policy makers, and in that being a scientific ministry, we also had interaction with the scientists, and we supported the research projects. So that's why I want consider myself to be an expert in any of the field, but to some extent, yes, there is some interest actually, which I continued as researcher. And whether my presentation is visible? Hello?
No, sir, it is not visible.
Oh, it is. What has happened?
Sir, again you go to that presentation, sharing presentation. I think.
That's what actually I'm looking at, where it is.
Sir, it will be at the right corners, or from where you can mute yourself. There is outward arrow, sir. Pradeep, sir, you did a few minutes before. So
Yeah, I did it. That's what actually I'm a bit.
are you able to see that outward arrow?
No, that's what.
Sir?
Yes.
Yes, sir. So you just, okay, are you able to see your camera, mic, and then there is a arrow, share content.
That's what actually I'm not seeing. That's share your screen. I want to share the screen, but I'm not.
Okay, if you are facing the problem, you do one thing, you again, okay, you leave the meeting and join again because you did it earlier.
Yes, I have joined.
Yes, sir. So, make him present. He's presented already. Just
Yes.
sir, you are presenter. So now, see, are you able to see that arrow, sir?
Yes, yes. If my
yes, it is visible, sir.
okay, okay. So sometimes the technology also creates a bit of problem.
Yeah, no, it's okay, sir. You did in the morning. Sir, you please hide that arrow. Yeah,
Yes.
thank you, sir.
Okay. Okay. So as I was mentioning that we had been practically the policy makers, and but yes, I had worked in Solar Energy Center for about 10 years, so did some research work. I started my career as a project officer, as was mentioned. So I'll just try to give some perspective actually of how the development have taken place and what actually where we are heading to. So practically we all have been talking about renewable energy and as well as also of the energy conservation. Now the word have been changed from energy conservation to efficiency, and this practically is due to the resource availability, what the resource available, entire resource, energy resources available with us. And as you all know that the world population is now increasing every day, and particularly this is very serious concern, particularly for the African and the India, where the population has been increasing quite fast. And simultaneously, the expectation of the people is also to have a better lifestyle. And if the better lifestyle is required, naturally, you should have the economic growth. And for that economic growth, you require to have energy requirement, because all your industries and the gadgets and everything, they will run on one or the other source of the energy, form of the energy. But recently, actually, for last 10 to 15 years, the driving force for the progress of renewable energy were not the consideration actually what I had mentioned earlier, that the resource availability or the world population, economic growth and all that, but it's more on the environmental issues and the commitment to the greenhouse gas emission reduction. So as regards India is concerned, India has made a commitment to the Paris Climate Agreement to reduce the emission intensity of the GDP by 33 to 35% from the 2005 level. And for having that, at least 40% electric power installed capacity should be from clean energy sources by the year 2030. So for that, an ambitious target of 175 grid connected gigawatt of the grid connected renewable power by the year 2022 was announced in 2015, which includes 100 gigawatt coming from the solar energy. In addition, of course, the wind and biomass and solar small hydro are also there. But in doing all this, the manufacturing is also being given specific attention, and focus on R&D is definitely there. But education and skill development, that is also one of the key consideration of the growth of renewable energy. This on the background of whatever commitment which India has made to the climate negotiation at Paris. So if we look at the energy resource or the sources basically from where ultimately the energy is coming, the sun is the ultimate source of energy, whether it is renewable energy or the conventional coal, oil and gas. Ultimately, the sun is the major source of energy. The only challenge actually when we talk of conventional energy sources, it's basically the process in which our biomass and all those things have got buried inside the earth, and then some process have taken place, and from there ultimately this coal, oil and gas, they are formed, and it takes about millions of years. So the challenge here is whether there would be a process basically in which million of year process could be reduced to a limited years. So that's what is basically the challenges which the scientists have been now pursuing. And in that process, of course, this coal, oil and gas ultimately the main source is the biomass, which particularly gets energy from the solar and through photosynthesis process. Ultimately, then they provide us the source of energy. So now the challenge is, as I mentioned, so what is being now done is that the solid thing, the coal is the solid. What should be the substitute of that? The gas, natural gas. So is there any substitute of that natural gas? And then, of course, the oil, the liquid. So in terms of when we talk about biomass energy, then we talk about different processes. It may be briquetting, or it may be pyrolysis, or it may be basically conversion of biodiesel or the ethanol, or the biomethanation process, the fermentation process through which the gas is formed, or the gasification process through which we get the gas, and then ultimately removing carbon from the hydrocarbon, basically the and getting hydrogen and becoming a source of energy. So that's basically, so ultimately starts from the sun, and now that the million-year process is to be reduced to a limited years or days, I should say. Like if we say the biogas, then it's a process of say something around 30-40 days, and if we work on say high rate biomethanation, maybe for in a controlled environment, then it can be even for 1 day. So that's how basically the process is going on. In addition to that, of course, the motion of and gravitational potential of sun, moon and earth, which is basically the source of tidal energy. And to harness the tidal energy, there is only one project at the moment in France. Otherwise, though India also has some potential here, but nothing much is being done in the area of tidal energy. And then the geothermal energy, there are some countries which are like the Iceland or Philippines, which have significant contribution in their energy, electricity generation from geothermal energy. In addition to nuclear reaction and the chemical reaction, the mineral sources. So these are the ultimate sources of energy. But sun basically is the main source of energy through which everything is going on. Now, in terms of renewable energy, when we talk about renewable energy, basically the solar, wind, biomass, or the gas, it is the energy which is obtained from the continuing or the repetitive current of energy occurring in the natural environment. Whatever we have been getting in the form of energy itself. The solar radiation are coming in the form of energy, which now it is up to us whether how to use that energy and convert that energy in the another form by using some methodology. While in the non-renewable energy sources, these are the energy obtained from the static stores of energy. Here the word store is important because ultimately these are kept somewhere in the form of a bank, and we have been extracting it, and that energy is basically bound unless released by the human interaction. Certain human interaction is required. If you have a coal, you can't do anything until unless you have a furnace and burn it. And similarly, the oil, you should have an engine through which basically you can generate energy out of it. So some human interaction is required. So effectively, in the case of renewable energy, the energy is coming from the environment, and environment is acting as a source, and environment is also acting as a sink. So whether we use it or not, that depends on us. But if we are accustomed to certain lifestyle today, then we require to convert this energy, whichever is coming, energy current which is coming, into a useful form, which can be heat or process heat, or which can be electricity. So you require a device or a methodology, and then through that human interaction intervention, you can use it, and then ultimately whatever left is goes to environment. So that's why the environment is acting as a source, and environment is also acting as a sink. While in the finite source of energy, you definitely have to have a device, and through that device only you can use the extract the energy and use it for some useful or productive purpose, and ultimately whatever is left that goes to environment. So that's why in both the process the efficiency becomes very important. Means how efficient our device is or how efficient is our energy harnessing methodology. So, so the factors basically which are to be considered for practical application of any energy sources. So, how much quantity of the energy source available in the environment? What is the availability of the resource? And then more important is the purpose for which the harvest energy is to be used, because that defines actually how efficiently basically we are using our energy source. Because sometimes it is said that if you have a thermal power station and from where you are generating electricity and bringing it to your home, and then using it for heating water using your geyser. So what will ultimately be the efficiency? Because in the thermal power station, your efficiency remains only 30 to 35%. And ultimately, if you take the T&D losses and then again converting it into heat, so whether it is a good thing or not. So that's why the purpose for which the harness energy is to be used is very important. So, and ultimately the price at which the energy is generated and what is the price you would be paying for that. So, but in terms of what is the availability and the reserves basically of the conventional sources, if you look at this is definitely an old slide. And if you look at the reserve, what is available in India and what is the world thing, and if you see the uh, just hold on. So, hello. So the resource availability about the divided by the production basically at the rate we have been producing it. If we look at that, then the coal is sufficiently available in India and so in the world also. But there is a problem as regards this crude oil. There is some disturbance. I'm seeing it. I do not know why. Hello. So the R&P ratio, the resource availability and the rate at which we have been producing it, if we convert it into years, we'll find that the conventional resources are limited for limited time available with us, and that's why that gives a necessity to work on the renewable energy side. So in terms of availability of the renewable resource, if we look at that, the solar radiation which are absorbed on Earth are something around 120,000 terawatt. That's the level of energy which is falling on the Earth's surface, and which is practically being if distributed in terms of 80,000 terawatt, which is basically used in sense of sensible heating, which could be utilized in the form if we have a suitable energy solar device, or the part of that is also can be used in the ocean thermal energy conversion process. Then, of course, the latent heat potential energy, the hydro resource, then the kinetic energy, wind and the wave conversion, 300 terawatt, that's the potential, and of course the photosynthesis, the biofuel. Then others are the geothermal and the gravitational orbit thing. So geothermal practically is giving heat, and from that heat we can have the electricity. Similarly, the tides, basically practically you get at least 2 tides a day, and then on 8th day you get the neap tide, and the 15th day the high tide. And if you use these tides to store water and then produce electricity out of it. So that's what is the total resource available in terms of world over. That is the huge thing which is available. So ultimately, it's the sun basically, which is practically can has the potential to fulfill all our energy requirement. So in terms of the solar energy utilization, if we look at this, then it's the direct method. The direct solar energy utilization method is basically there are two methods. One is the thermal, wherein we use the heat part of it, and then the photovoltaic, wherein we convert the solar radiation into directly into electricity, and then we use it for whatever purpose the electricity is used at present. So in terms of thermal, if we look at the thermal can also again be distributed into two parts as far as the application is concerned. One is basically the low grade heat. Whether we use one sun means at a point only the one ray of solar radiation is falling. So ultimately we use in the thermal, practically the term we use is the collector. So the solar radiations are collected. So in terms of material, if we talk in the thermal, then you should have the material practically a metal which is a good conductor, and then so that the uniform distribution of the heat takes place in the collector, and then we have to absorb actually the radiation available. So there should be the coating which should have good absorbability, and it should have low emission, basically emissivity should be less. So that type of material is used, so coated on the metal, so that the maximum heat is collected or the generated, and whatever heat is generated ultimately that has to be captured in the form of a cabin or an enclosure. So that's why you require to have a material which should be transparent to the lower wavelength, but should be opaque to the higher wavelength. So that's basically the glazing, the good transparent glass. That's the material basically which is used, and then whatever heat and enclosure, which we say the greenhouse effect, basically we create a greenhouse effect. So in the lower range of heat, practically an enclosure is formed, and in that enclosure basically we collect the heat and then transfer that heat into a liquid, and then use for whatever purpose. It may be hot water, or it may be the dryer, or it may be practically the air heating, room heating. That sort of application can be done. And the second method, basically when we concentrate the solar radiations which are coming, so these concentration practically again are is being done through two methods. The one is basically the dish in which we have the point concentration. So in place of one sun, we can have multiple suns at a particular point. All the radiations are falling at a particular point, so the temperature goes as high as 600, 700, 800 degrees Celsius, and we can generate steam out of it. We can run a Stirling engine, and we can even produce hydrogen. So whatever that method is practically. And the second is the parabolic trough, basically, wherein it's basically the line focusing sort of thing. So all these, the thermal application, practically the material being used is the metal or the metal and the coating material basically, which we use the black chrome sort of thing because the coating whatever we do, that should also have basically a life which should not deteriorate at a higher temperature. So that's what is the thermal application. And practically if you look at the distribution of energy, because what happens actually sometimes we start with energy but unfortunately confuse it with the electricity. So the focus today is totally towards electricity generation, and to some extent the efforts in harnessing the solar energy for various thermal applications. The process heat part of this is not taking that much of attention, which particularly we have to think actually how this thing could be revived, because ultimately it's hardly 20 to 30% of the total energy requirement is fulfilled by electricity. The rest is basically coming from one form or the other is the thermal. So if we can work on the thermal field, that would definitely be good. And that's why I'm specifically putting some emphasis actually on this aspect. Of course, this is more on the engineering side, basically, that how you design your system. But on the material side also, there are a lot of things which could be done in the form of finding the new materials to have good absorbability and less emission through it, or the better coatings, and the glass material basically good reflectors. So that these are some of the aspects basically where the material science can play a very important role. But as regards the photovoltaic is concerned, that's basically a method wherein the solar radiations fall on a device called the solar cell, ultimately which is directly converted into electricity. And once it is electricity, then you can use it in any form. So ultimately, see, as I mentioned, it's the source, sun is the source of energy. So how we get this thing, the solar radiation, some data are there. That sun is about 150, 149.5 into 10 to the power 6 kilometer far away. So the solar radiations which are coming on Earth, it subtends an angle of 32 minutes, basically a very small minute. So if we look at, because it's a quite large distance, so at a particular point, the solar radiations which are falling actually can be treated as the parallelly falling on a point. So that's what we say the direct radiation, the solar radiation that reaches the surface of the Earth without being diffused is called the direct beam radiation. And then the radiation, the other radiation part of the sunlight that pass through the atmosphere, some of it is absorbed, scattered, or reflected by the air molecule, water vapors, clouds, dust, and the pollutants from power plant, forest fires, volcanoes. So, in fact, it's not the direct route basically that gets scattered or absorbed or whatever it is, ultimately the attenuated, and that is called the diffuse radiation. So in a typical cloudy day, we get more diffuse radiation. In a typical sunny day, like nowadays, we get more the direct radiation. So if we are working in a concentrated form of utilizing the solar energy, then we should have good direct normal incidence and direct radiation. But in the photovoltaic or even in the flat plate collector, in the solar thermal application, both direct and the diffuse radiation both are used. and the sum of these two are called the global radiation. So practically the solar constant. So as I mentioned that whenever the solar radiation are coming, falling on the Earth's surface, so part of that is basically absorbed by the layer, which is the ozone or the carbon dioxide or the water vapors available in the outer atmosphere. So outside the atmosphere, basically, we get a radiation of 1367 watt per meter square, which is called the solar constant. But on the Earth's surface, particularly at the equator, we receive something around 1000 watt per meter square. That's the radiation we have been getting. And this is basically the main thing which is used for in fact characterizing any solar device or solar cell or module or the array, whatever it is. That 1000 watt per meter square is taken as the standard basically. So, but the solar radiations which are coming on Earth, they are not uniform actually throughout the year. As you all know, the sun, the Earth revolves around the sun, and it takes around 365 days to complete one revolution. So there are four typical positions. One is two positions which we say the equinox, which comes in March and September. And practically these two are the days basically which becomes the reference for us to actually, when we design a solar system and we find that what should be the tilt angle of their solar device actually to have the optimum output out of it. But on the summer solstice, basically, which is on June 21st or 22nd, when we say that so the longest day, and then we see that the solar radiation basically falling almost means perpendicular to Earth, and on typically on in the month of December, it's basically quite slant. So that actually gives us some idea about whether we can have some sort of tracking basically to make the system more efficient. So that's basically the part of the engineering. But a very important aspect basically which we have to take into consideration while designing a solar system or solar device. Now, basically, basic Earth-Sun angle for calculating solar radiation and designing solar device. The knowledge of sun's path in the sky on various days in a year at a particular place is the prerequisite. So this is basically as far as the design part is concerned. So we have the solar altitude angle and the solar azimuth angle. These are the two coordinates locating the sun in the sky. So where the sun is and how the radiation will fall on a horizontal surface. So these are the two parameters basically which are taken into consideration. So the apparent solar path in a particular day is shown in the figure which I'll be showing basically, thereby showing sun's zenith angle, means when the sun is on the overhead, then the altitude and the azimuth angle. And the altitude angle of the sun is defined as the angle in a vertical plane between, let me come here. So this is basically this is suppose the Earth's surface, and this is the east-west direction. This is the north-south direction, and this is the reference point basically where we are there basically, practically any device or anything is there. So, and the sun's position is this. So this is the vertical. So the angle subtended between the solar radiation sun rays direction and the vertical direction, this is basically the zenith angle. And this device, this will have the solar, it's basically what we say, the image basically which is now forming. So the angle between these two, this is basically the altitude angle, and ultimately, and this is the azimuth angle. So that's what actually is the azimuth and the this thing, and these things are very important actually in defining the actual angles basically which we have to designing a system. So if we look at the sun's structure, basically it's basically a thermonuclear fusion structure, wherein the hydrogen, two hydrogen atoms basically forms the helium, and in that process the fusion reaction takes place and the energy is generated. And that energy basically on the temperature at the core, it's very high, but if we come to the surface, ultimately it becomes something around 5,900 degrees Celsius, which are basically radiated and coming to Earth. And if we look at the spectrum, then the spectrum has all the wavelengths, visible light which we see, and then the infrared which we feel, and the ultraviolet, most of which is basically absorbed by the ozone layer, and the X-rays and the radio waves. So practically, so Earth is surrounded by an atmosphere containing various gases, dust, other suspended particle, water, vapor. So whatever radiations have been coming, that gets attenuated, and then ultimately what we would be getting, the ultraviolet, very small part, around 6% of the whatever radiation is coming on Earth. The visible radiation basically which we see, which is around 48%, and the infrared radiation, which is basically the 46%. So ultimately, this radiations which are coming, ultimately it is practically a sort of black body radiation. So if we look at the outer atmosphere, it is something like this. But when it gets attenuated, ultimately we get the radiation like this type of radiation, which is practically being used. So this is the same thing. So ultimately, this is the ultimate distribution. So when we make a device, or when we use the solar characterization or anything, we see that at what angle actually the solar radiation is coming. See, ultimately, if we look at the solar radiation in the morning, if you see the sun, the sun ray travels the maximum path. At the noon, it is the minimum, and the evening again it becomes the maximum path. So how much actually within the atmosphere, how much length actually it covers? So that determines actually what would be the spectrum of the solar radiation, which we say the air mass in terms of air mass. So the air mass 0 is the extraterrestrial, means the outside the Earth atmosphere. And as a reference, we take the AM 1.5 spectrum, which is practically this spectrum, which is something around 48 degrees. So if the solar radiation are falling on the surface at 48 degree, what would be the spectrum? That spectrum is being taken as the reference for characterizing any solar cell or the module, and that is the basically the standard we use. So whenever we characterize a solar cell, module, or an array, because ultimately the solar cell gives an output which we say how much wattage. We never use the word watt, basically we use the watt peak. So what is the basically total rating of that solar cell or module or the array? It's basically the watt peak, and we pay the price for that. And because the solar radiation is not uniform throughout the day, or if we say it in terms of months or in terms of say seasons. So what should be the criteria? So the criteria, so a standard criteria has been, now standards have been set that we should have 1000 watt per meter square. That's the radiation basically, which is falling on the device. And that spectrum of that solar radiation which is falling on the device should correspond to spectrum AM 1.5, and then the temperature should be 25 degree, means the 25 degree temperature of the cell. So at that time, what is the output of that particular cell? That is the rating at which practically we pay the price of that device. That is the standard thing, which it's very rarely basically if I have a say a 300 watt module. So in practice, whether I will be getting a 300 watt or not, that will depend upon how much radiation is available, at what angle it is available, and what is the ambient temperature. If the ambient temperature is high, then the cell temperature actually becomes higher than that. It is because of the characteristic, material characteristic, which is something around 23 degree higher than the thing. And as the cell temperature is more, then ultimately we get the lesser efficiency of that. So that's the spectral distribution. I've already covered this aspect. So in terms of the air mass, as I mentioned, so how to measure the air mass? This is basically how we measure it. Suppose this is the device, and solar radiation is coming from this place, and this is the zenith. So what is the angle basically which is formed between solar radiation and this actual path length traveled by the solar radiation, and the ratio basically of the actual path length traveled and when the sun will be on the zenith. That is basically the determines the air mass, which is basically the set value of theta z. So AM0 is when it is outside the Earth atmosphere, AM1 is when the sun is at the zenith, and AM2 is when it is the zenith angle is 60 degree. But AM1.5 is somewhere when it's basically 48.2 degree. This is basically the air mass 1. This is the air mass when the solar radiation is overhead on the zenith, we will get the air mass 1. And for reference purpose, we take as if the solar radiation will fall on the device at AM 1.5. So to measure the solar radiation, practically we use different devices. So incoming solar radiation which are coming, part of that are reflected and part of that are absorbed. So we would be getting both direct beam radiation which are coming directly and falling on the Earth's surface, and part of that are which are basically coming from different directions through sputtering or absorption and all that. And so the global radiation will be the sum of the direct radiation and the radiations which are coming from different directions because of the scattering and diffusion of the solar radiations from atmosphere like this. So ultimately, this is the thing. Ultimately, this is the direct radiation. Part of this are reflected, and these are coming through diffuse radiation. So in terms of how these are distributed, so when the cloud cover is there, a typical cloudy day, we get more the diffuse radiation, which are of the order of 200 to 300 watt per meter square. When a partially cloudy day, we get in a typical situation like particularly in the northern area, India, we have been facing during these months when this parali is bird basically, and a haze is also there in the atmosphere. So at that time, practically we get the radiation of the order of 400 to 600 watt per meter square. But when the clear sun is there, then we get as much of as 800 to 1000 watt per meter square. So that is how the distribution is there. So in terms of solar radiation, what is the availability of solar radiation? Availability of the solar radiation means world over the resource wise. If we look at how much is the total solar radiation means in terms of kilowatt hour per meter square. If we look at that, then there are places like Africa or the Gulf area and part of US and this South America and Australia. These are the places where you get a good intensity, and it's more than 2200 units per square meter, means kilowatt hour per square meter. That's the total intensity of the solar radiation basically, which is falling on Earth's surface. In India, practically, if you look at that, we fall somewhere around 1900 to 2200, which means if you take 365 days, it's around 4 to 6 kilowatt hour per meter square per day. That's the basically the intensity of the solar radiation, or that's the total energy, I should say, in terms of per day, how much the total energy is used in a day. So we fall somewhere here, and if we go towards a bit north, then it's around 1700 to 1900, means around 4 to 5 units of the solar radiation, basically kilowatt hour per meter square. So that's the availability. So in a sense, what we say that we have sufficient solar radiations available to throughout the year, barring a few days, except in the northeastern areas. In the rest of the country, we get a good sunshine for more than 300 days. And that's why we have good potential to use the solar energy. So now in terms of when we come to conversion of solar radiation into solar electricity, Then, of course, the phenomenon which is called the photovoltaic effect, I do not know it's really an effect or whatever it is, but yes, it's basically the photovoltaics. The photo means the photon plus the voltage. Whenever the solar light forms on the device, it's basically the name is photovoltaic gives an impression about the voltage, but practically it's a current device because ultimately it's the current which is generated and the voltage becomes the characteristic of the material being used in that device. So ultimately, see, these are the advantages. It's a clean, reliable, efficient device, and it's possible to have mass production. So technology is available. Pollution free, no pollution is there. As I mentioned, now the driving force, which was at one point of time when we started and when there was an oil shock, actually first oil shock in 1973, and when this oil exporting countries, OPEC countries, had increased their oil price to 400 times of the price suddenly. So in a day means the entire economy of most of the countries got disturbed. And then a feeling came that can we work to have the energy independence? And that's how the renewable energy movement practically started to get an energy independence, so that we do not become dependent on some of the countries who have large reserve available of the fossil fuel, practically the oil. And from there, actually, this development started. And if we look at how the technology developed in terms of solar photovoltaics, see in 1954 when the Bell make the first cell of 4% efficiency. Today at commercial level we see the cell efficiency of something around 21% and the module efficiency of 18 to 19% now possible at commercial level, what we have been seeing. And the advantage, of course, means at that time, as I mentioned, the focus was the energy independence. But later on, practically now today, the driving force is more the climate aspect, and that's why it's characteristic of being pollution free, no ecological problems basically if we generate electricity by using the photovoltaic devices or photovoltaic systems. So, and practically the photovoltaic system has device, particularly the modules, have long life. We say something around 25 years. And it doesn't have any moving part, and if the moving part is not there, so the wear and tear is less. So that's why you require little maintenance. Practically, these are light also if we particularly work on the thin film thing, and power to weight ratio is very less. And we can have high material utilization also, 100 megawatt per meter cube for the thin film solar cell. And for silicon, it's 120 kilowatt per kg. That's what we can get at least from 1 kg of silicon. We can have 0.5 in a sense 5 watt, that much it's possible to produce basically. And the best advantage actually it's a modular nature, means that you can have a milliwatt system, you can have a megawatt, and now we have been talking about in terms of gigawatt, wherein the a centralized power plant of having 1000 megawatt or 2000 megawatt or even 5000 megawatt electricity generation. So it's a modular. You can have a very small device as we have been using in our watch or calculators and all that. And then we can have for a home system, we can have for a campus, we can have for a large township. So it's modular in nature, and then it is standalone also, localized, so portable power pack, no transmission problem. So that can also be treated as one of the characteristic of the photovoltaic. Practically, why I am telling all this, while all these advantages are there, to some extent, the way the developments are being taken place, actually taking place nowadays, it's basically something different than whatever the advantages of this technology should have been, basically, because now the focus has totally shifted actually from a decentralized power generation using photovoltaic to a centralized power generation, where we are having a power plant of something around 2000 megawatt, 3000 megawatt, 5000 megawatt sort of thing, and from where the electricity is generated and transmitted to different places. So the context actually in which we have been talking, or initially we were being told or we learned actually that these are standalone in nature, so you can produce the electricity wherever you really require it, because the strength of the solar energy means the limitation is it's a weak source of energy. The intensity is very low, but it's the dispersed source of energy, so we can generate electricity at the point of use also. So the context is now to some extent have totally changed, and that's why in terms of utilization, it's a bit different, and that are posing certain challenges to which I'll be coming later on actually. Then integratable, now integratable in the sense that you can integrate it, whatever power is generated, so that power, that electricity can be integrated with the other electricity system. It's basically what we can say a hybrid system. So the standalone practically is a system wherein the electricity generated from the solar photovoltaic module or the panel or the array. So that is used in a standalone, means only that electricity, either you store it and use it in a 24-hour profile, or you don't store it and use it instantaneously, as you can do it in the pumping process, that type of application. But it is integratable, so the hybrid in a sense that you have a grid, or you have a diesel power generation, you have a wind power generation, so you can integrate the power, club the thing, and can optimally utilize your system. The other advantage is the variable voltage. So you can have, as I mentioned, that you can have a very small system like we use in our watches, calculators, and all that. So the voltage practically, if a typical silicon solar cell, if you say only cell level, you say, so you get something around 0.5 volt. And nowadays the current is of course coming 4 ampere, 5 ampere, 6 ampere, that type of current you can generate. And then if you integrate that cell into form a module, then you can generate a voltage of something around 18 volts, 36 volt, 72 volt, or 96 volt. And then if you integrate the modules into parallel and series and parallel, then you can have the voltage, variable voltage, means whatever voltage you want, you can design a system. So that's an advantage basically of this technology, and of course social and economic benefits in terms of employment, because you get huge employment if you have you use the decentralized type of applications. So practically, in terms of solar cell, if we say it's basically the semiconductor device, which practically, as you all know, you all are material scientists, which I am not. But practically, the three types of thing: the insulator, semiconductor, or the metals. The metals where the valence band and the conduction band overlap, and the insulator where there is a huge gap between the valence and the conduction band. But there is the intermediary thing where the band gap is such that if you give certain energy in the form of maybe some heat or some particular wavelength, then the electron can be excited to from valence band to conduction band. So the valence band, the holes are created, and then the conduction band, you get the free electrons, and that free electrons, if you make a circuit, then you get you can have the electricity. So that's basically the intrinsic semiconductor material. Practically, what we do in solar photovoltaic, practically in place of intrinsic, we use the extrinsic thing, wherein it's basically a diode. In the P type, we have me artificially create the hole, and similarly in the N type, we artificially create an excess electron. Practically in the silicon structure, if we take it's the fourth, means the outer ring, it's basically the 4 electrons. And if we dope a N-type material, so but in the structure, when the N-type material hits, there is one extra electron which is left, and then the P-type, basically we have when the boron is there, then we get only a hole, basically, because we have a deficiency of it. And when we intermix with these two, and then we get practically this type of structure, the P type and the N type, and then the diffusion takes place. So ultimately, in the N type structure, at the junction level, we get more holes, and at the means that the holes are there, and in the P type, practically at the junction level, it's basically the electrons are there, which practically works in basically separating the charge when the solar radiation falls on it. So that's how it works, and you get practically the electron hole pair, which are basically separated because of the potential field basically which is generated in between. And then when you make a circuit, basically, so the electrons means the circuit is completed, and you get the electricity generated. So practically looks very good, but in terms of material, different technology materials are there. The prominent being the silicon material, which is basically silicon single crystal. Now we get the cells of around 4 square meter, and the efficiency, the maximum efficiency which have been achieved is 24.7 volt, percent efficiency we have in the single crystal, but at the commercial level, it's something around 21% that is achievable. And in fact, the technology which is used basically in this 24.7, which is the market, what we say the Martin Green technology, which was basically also used by the Central Electronics Limited, and they can go up to 19% of the cell efficiency. And the silicon multi-crystal efficient crystal nowadays 6 square meter, 6 square inch basically. That's the commercially available cells are there in the market, and we get an efficiency of something around 20.3%. Then the amorphous silicon single junction, the efficiency is 12.7%, and the triple junction again 12.1%. But the amorphous silicon junction has the problem of stability, while the triple junction are giving good results. The cadmium telluride, the 16.5% efficiency, the CIGS. Practically the 9.5%. So the multi-junction we can get up to 40.7%, and the hit type of thing the 21.8. So that's what is the cell efficiency which have been achieved world over. And as far as the India is concerned, we have the capacity of means the efficiency of 18%, to some extent 19% now, as I mentioned in the got by the CEL. But at commercial level, effectively the cell efficiency what we have been getting as on today in India is 16 to 18%. That's the level basically which we are getting, but we are hardly working in amorphous silicon or the other technologies. Means these are mainly at the lab level basically, where the work which is being done. So this is how basically the solar cell is formed, from the sand to polysilicon to crystal ingot to wafers to cell, and ultimately these cells are series connected to form the module to have a particular voltage. Nowadays, if we look at the typically we have 36 cells module, we have 72 cells module, and we are also having 60 cells modules. 60 cells module are practically being used in large power plants, and so that's basically the how the solar cell is being manufactured. This is basically I have just taken. I'm not much aware of all these things. So practically in a solar cell to module, what we have, as I mentioned, is the glass surface, and then we have the EVA label, anti-reflection coating, the transparent adhesive, which we say the EVA, and EVA, that's again a material and which should have the refractive index exactly that of glass. And whenever you basically encapsulate that, means it should become totally transparent. And then we have the cells, and make a hole and we have the bulk material at the bottom, and then we have a thin layer. So practically when we started actually the solar cells, it was something around 300 microns. So now at the commercial level in the crystalline cell, we get something around 100 micron. So that's more basically on the engineering side because of the methodology of cutting the angers into forming the vapors. As far as India is concerned, we practically are not doing anything as far as working on the material side, particularly forming the silicon to ingot. That part is not there. In fact, we all either have been importing the wafers or we have been practically from wafers are either making the cells or ultimately when we are directly purchasing the cells and making the modules in our country. So that's what is the typical crystalline silicon solar cell efficiency. And there are different losses, which are basically the thermodynamical losses, the optical losses, or the electrical losses. So what is being done actually to improve the collection efficiency? What we say, the when the solar radiation falls in it, it should whatever radiation is falling, that should remain there. So ultimately, so some structure is being made, which is basically called the group type of structure, which is basically used by the Martin Green technology. So the solar radiation which is falling, it in place of getting one thing, sun, so part of that the reflection, so it is again absorbed here and then goes there. So ultimately we get more efficiency because the more solar radiation is absorbed here. So this is the basically the texture, the structure basically which are being used by the Martin Green technology, and then ultimately the how you means whatever the electron hole pair are generated, they need to be collected also, and that's why the buried contacts are made so that the recombination doesn't take place. So that's what basically the texturing and all those things are done. So in addition to that, the nowadays the high efficiency silicon solar cells are also being used. So practically, if we look at this thing, so how the technology have changed. So initially it started from the crystalline solar cells, then it went to thin film solar cells, and nowadays we have been working on the dye sensitized solar cells and then the perovskite solar cells, or different types of technology which have more efficient. But in the commercial level, if we look at commercial level, still it is the same crystalline silicon solar cell which are dominating and which are being used. Practically, why I am telling now all this and what I said that what would be the ultimately the challenge which we will be getting. Unfortunately, the slide is not there. See, practically you look at the focus, as I mentioned today, it's on the generation aspect only, and we have to have 100 gigawatt of solar electricity generation from solar energy. That's what is by 2022, and which is almost in line, which the goals are there. But by 2030, we will have 450 gigawatt. That's the total electricity generation through renewable energy. So a typical challenge basically which we have been getting from solar, the challenge, where the challenge is, this is Hello, this new slide is being visible?
Yes,
Yes,
sir, it
sir.
is visible.
Yeah. So if you look at this, so this is a typical generation pattern of a month. In the month of May, from a small power plant, practical results are there, and you see the generation is very low here on the 11th of May, while the typical generation is something around from a 12 kilowatt power plant we are getting uh, yeah, around 50 kilowatt hour here. And what we really expect from solar is something like this. This is a very smooth curve. That's what we expect. But practically what we are getting is this. This is on 31st May and this is on 27th May. Now, that is one challenge. The another challenge basically which we are expected to face is basically there is a base load, and that base load is being fulfilled by mainly by the thermal power station. So today, whatever is our demand, if you look at, if you have downloaded the Vidyut Prabha app, actually you can practically see that our demand is not increasing. Practically it comes within 140 to 160 gigawatt practically at a means that's the demand at maybe at around 12 o'clock. So at 12 o'clock, you have something around 260 gigawatt thermal power station, and if you run that at 50% efficiency also, so you will have something around 130 gigawatt. That's the minimum level basically which you have to produce. And then at that time, if you will have something around 100 gigawatt of solar generation, so ultimately you will be having something around 220 gigawatt of total electricity available at that time, while your demand will be only 160. So what you need to do is you need to reduce the thermal power generation at that time, which is not good for the health of your thermal power station also, and it's also not good. So what should you do basically? So that is the context actually in which the storage is now being talked of, that when you have the surplus power. See, remember the situation now is we are not the electricity starved country the way we had been thinking or we had been progressing some 10 or 15 years back. Today, at some point of time, we have surplus electricity available. And the surplus electricity which is available is not again uniform, because as you may see from this particular graph actually, that's the generation. And the another challenge basically it's not the generation from one single plant. So the multiple power plants. So your transmission line should also have the capacity to absorb the entire electricity generated at a particular time. So whether your transmission system is mature enough or the capable enough to absorb everything. It is something like you have a large river like the Ganga, and which have a number of tributaries available. So all the water flowing from the tributaries ultimately merge to your main river, and main river has the capacity to absorb the entire water. But during rainy season, when the flood is there, so it means more water is there in your main river as well as you are getting from the tributaries. So the flood situation comes. So similar situation may arise. To some extent, we have started facing this type of scenario when you have surplus electricity available, and then you have a regulation called the must run. Means the renewable source must run, because you don't spend any cost for the fuel, because fuel is coming from the atmosphere. So at that time, when such type of things come, how to address all this? So in this context, actually now we have been talking about the storage and the context in which we have been talking about storage earlier. That's totally different. Earlier, we have been talking about storage in a sense that when the surplus is available, you just store it and use it when it is not available. But nowadays, you have to address this thing. So the storage system should have the capacity to respond quite fast, and the power density of your storage system should be quite high. And when you have to ramp up, because in the evening time when your peak comes here, your thermal station also has to ramp up, and that thermal station cannot be ramped up. Today we have been using the hydro thing to manage to balance all that. But when this situation will be a bit different, you will have more demand suddenly increase. So you should have whatever surplus available here that should be stored and that can be utilized here. So in this context nowadays, we have been talking about the storage, and in this context also to some extent when the electric mobility and all those aspects we have been talking, where at daytime when suppose I go to office and keep my car there and put in a charging mode, but suddenly it happens that the demand increases. So that storage can also give back to the grid. So what type of storage material should be used? What should be the technology? That's very important. So the context actually in which we have been talking of storage and the context in which we have been talking of integration, these are entirely different than the context in which we have been talking all these things earlier. Because now earlier the concept of solar photovoltaic or the solar energy, or for that matter any renewable energy sources, it's basically a weak source, and the dispersed source should be generated at a point of use. But today the situation is it is being used as a conventional system wherein you have a bulk power generation at one point and you are transmitting it. So that entire transmission system gets overloaded. So how to reduce that? So should you have a storage device at the generation point? Should you address the frequency regulation part of that in the transmission system, or should you use it at the application use point, as we have been doing even nowadays? So these are the things basically which are very important, and these challenges actually needs to be addressed. So the challenges are the intermittent nature of the renewable energy. That's basically the challenge, and that should meet the demand and supply mismatch basically, which is as I mentioned just now. You have the surplus electricity available at a particular time because that needs to be stored in some form. And when we talk of storing actually at that time, so it is practically working as a load for that. So your storage device should work as a load when you have surplus available, and then it should act as a generator when you require electricity. And then you should also have the capacity to address the sudden suppose the cloud comes suddenly and your generation reduced to the lowest level. So how your storage acts at that time? So you require the energy intensive storage mechanism also, and you require the power intensive energy storage. And another challenge basically what we have been talking about, the 24 hours domain, how this power supply can be utilized. Again, the storage becomes very important, and that's why the storage, when we have been talking and the multiple storage mechanism, it is not only the batteries, but we have been talking as the supercapacitors or the capacitors, and then we have been talking about compressed air, we have been talking about liquid air, we have been talking about pumped hydro, and all those basically are the part of storage mechanism in which the storage mission basically are being formed. And energy, so that another problem of energy congestion in the grid could be addressed, and there what should be the role of storage basically, and what should be the materials used in that. So that's what it is. So the vision for to have 450 gigawatt of the renewable energy by 2030. So all these challenges basically need to be addressed basically before we go for that. So that's what I wanted to say. I'm open for questions now.
Thank you, sir. Thank you very much.
Hello.
Hello, am I audible?
Yes, sir.
Thank you, sir. Thank you very much for enlightening us with your very important talk. You covered all the basics of photovoltaics, and you explain us the working of photovoltaics and other informative things. So now this talk is open for discussion. So I request the participants who has joined us through this Microsoft team, please raise your hand to ask the question. And at later we will take the question from our YouTube viewer. I request the participants, please ask the question. Okay, Manpreet, you can go ahead and ask the question from our YouTube viewer.
Okay, sir. So there is one question. Please explain. We have enough water in our coastal areas as sea water. Why are we not concentrating to use photocatalyst for water splitting and generate electricity from hydrogen?
See, practically this hydrogen generation of hydrogen using means the electrocatalytic method basically, this is being tried actually at our National Institute of Solar Energy. They have started working on that. Practically what I am telling is say today it's the technology is not that mature actually that we do it, but ultimately in maybe 10 years down the line, I should say, the situation will definitely be such that that the hydrogen will become the mainstream fuel. Today, it's not the mainstream fuel. Rather, it's not a fuel as such. It's hardly some experimental work is being done. But ultimately, see, when you use hydrogen in the form of, say, transport fuel, or for that matter, any fuel, basically, ultimately what you get the water. So it there will be hardly any loss. That sort of thing is there. So whatever is available, it's basically the time. See, look at how the development have taken place. In your conventional electricity system, it took something around say 200 years to develop. Okay. So and if you look at the renewable system somehow, as I mentioned, that practically the focus on the renewable system started only in 1973 when the first oil shake took place. And initially it was basically for the decentralized sort of applications using your subsistence mean, and later on as the problem of this climate change and all those have become very serious basically, and then we thought to have going for in a large way for solar power generation, not only solar basically, but also the wind power generation. And now there is a situation when we can think that yes, we will have surplus electricity available with us. So what to do with that surplus electricity? So as I mentioned that you have to have a load available at that particular time. So whether that load could be to split water or to store it in a battery or to pump water from a lower reservoir to a higher reservoir so that you can produce electricity at any point of time. So these all are the aspects in which the work is going on and the policies are being framed. So hydrogen roadmap is also there, and we expect maybe by 2030 or 2035, definitely hydrogen will also, if not the main, but a significant role it will play in overall energy mix.
Okay, sir. Thank you. So there is one more question.
Yeah.
As you mentioned regarding the various technologies for efficiency of solar cells, which technology is more efficient and plentifully available in India right now?
As far as India is concerned, see, as I mentioned, means it's practically for the solar photovoltaic. Means the question is, I presume. Hello.
Yes, sir.
Yeah. So in terms of photovoltaics, if I say, as I mentioned, that in India, practically whatever developments have taken place, that's more on basically the crystalline solar cells only, and that is the only solar cells basically which are being used. But yes, work is going on heterojunction intrinsic thin film solar cells. The IIT Bombay, Ajay Agrawal group, they have been working on that, and then even this amorphous silicon, that's IASC Bangalore group, that has been working. And then, as I mentioned, the University of Cochin, basically Dr. Eldon Anthony, he has been working on the colored cells. So all these things are going on practically. But as far as India is concerned, as far as use is concerned, it's basically the amorphous silicon, crystalline silicon solar cells, and that too the multi-crystalline solar cells. The technology wise, yes, the technology, single crystal technology with grooved surface, that is available with Central Electronics Limited, the Martin Green technology, which they have basically taken from by collaboration with Australia, which, as I mentioned, they could achieve an efficiency of to 19%. But the commercial level, if I say, still we are going somewhere at 17 to 18%. That's what is available. The second thing is whatever the manufacturing capacity available with us, basically they are means it's the not that advanced, I should say. Yes, the new plants which are coming, they have been using the new methodology. Otherwise, it takes time basically. But it's the crystalline silicon only.
Okay, sir. Another question is, sir, how cogeneration technique enhance the power supply of photovoltaic?
It's not practically the cogeneration. Actually, the word used there is not correct. Actually, the cogeneration is practically the process heat and the electricity generation, which is mainly in the thermal thing. It's the word which was used there is not correct. The correct word should be the hybrid, basically, and that's what is actually happening today. See, ultimately, what is happening? You look at, see, I have a solar power plant on my roof, which has practically a solar photovoltaic panel. of capacity of about 1.5 kilowatt, and then the electricity which is generated actually it comes to what I say power conditioning unit, which is the inverter I say, and it has now, if you look at, then there is a storage device which is called the battery is also there, and then it has the input from grid also. So practically what I am using, it's a hybrid device, and how it is working, that the logic basically which is being used here is that at daytime when the solar radiation is available, my entire system goes towards the solar, means whatever is generated from solar, either it is used for my critical load, or if the solar radiation is not sufficient, say suppose take a situation of say 1 o'clock in the morning, I do not have sufficient generation at that time, while I have significant load at that time, because most of the household chorus actually that takes place at that time. So whatever storage is there in my battery, basically part of the electricity is coming from the battery and part of the electricity is coming from solar. Okay, and my grid is not being used at that time. And as the solar radiation means the intensity of the solar radiation increases, most of the solar part at daytime, it's basically whatever surplus is available that is stored in battery, and my critical load is being used, is serviced by the electricity generated from solar. But as the evening comes, when there is no solar radiation is there, so practically my system goes to grid. So my entire system works on normal grid available. So ultimately, it's basically a sort of hybridization of solar and means the electricity generated from solar and electricity generated from conventional grid. So a hybrid system. So you can have a wind system generation. So from wherever the electricity is coming, so you can hybridize it. It's basically that type of system is there. Practically what I want actually, but that's again part of engineering basically, and which I have been telling to many of our researchers working in basically the logic circuits and the electronics, are to form a device basically, because in my system it's the grid, the export is not possible, but in a conventional system which are used in a large power plants, practically whatever electricity, say suppose if I have a rooftop solar, I showed you the reading of means the generation from 112 kilowatt power plant, which is basically one of my relatives' home. So what is happening at daytime basically, whatever part of the solar radiation electricity generated is being used at home for the captive use, and whatever surplus is available that goes to the grid, exported to the grid, and in the evening time the entire load shift towards grid. So that type of hybridization is possible. So what I wanted actually been not in my circuit, but basically for the researchers, a challenge basically that my battery, my storage should be used minimal, and whenever the sufficient electricity is not available, I can take from grid, and my battery should be minimally used. So it's not the cogeneration, it's basically the hybrid basically. The cogeneration word is wrongly used there.
Okay, sir. So one more question from a participant. Are perovskite solar cells better than silicon-based solar cells?
Definitely. But practically when these solar cells will be converted into a practical module, because the making cell is one thing, but converting that cell for a use point in a module and then practically to use in a system, that's basically still far away, maybe 3, 4, 5 years down the line. But the perovskite solar cells are definitely better.
Okay, sir. So there is one last question. What is the availability of silicon on Earth, and how can we reuse these used cells of solar panels?
Uh, See, availability of silicon, uh, it's abundant. Silicon is nothing basically, it's the sand basically from which we have been getting. So, but the second question basically which you have been asking basically, it's basically recycling of the solar modules. That's really an aspect in which I don't think much work is being done because see how it happened actually. If you look at it was a sudden what I say uh, sudden jump actually. See when you initially till maybe 2005, 6, 7. If that time, if you look at your use of solar photovoltaics for power generation, real power generation basically, you leave aside your decentralized application, which basically nominal, nothing very serious basically at that time. So it never thought that how what will happen maybe after 25 year or 30 year from these waste modules and all that. But now because so much of deployment is taking place, so this aspect is also getting attention because it's basically not only of the silicon. Basically, the question is what will you do of that toughened glass basically, which is used as a glazing. What how will you recycle your EVA? How will you can you extract the basically the silver metal used for forming the grid over the solar cells? So these all are basically the new areas basically in which the work is going on. But as far as the silicon availability of the silicon is concerned, or the availability of the extracting silicon out of the solar cell or the solar module for that matter, because practically when you design a system, it's the solar module basically which becomes your basic building block. So whatever recycling that has to take place not only from silicon, but also you also have to see how you use the glass, how you use the how you can extract the metal, basically the silver metal which is being used for forming the grid out of it. That is also the another area. The in terms of material science, because most of you are the material scientists, say the another challenge basically is basically the wiring being used in solar systems, and the insulator being used in that should be the UV resistance. So how efficient that system is basically, that is also very important basically an aspect. Yes.
Sir, should I add something?
Yeah, definitely. Definitely.
Lovely. I want to say a few things about this recycling of the silicon.
Yeah.
Basically, in this solar photovoltaics, we are using single crystalline silicon, and once it is damaged, you have to grow the single crystal again. And as I understand, the growth of that single crystal again is very costly as compared to buy it, I think, because
It's
because
energy intensive also.
we are not having good quality single crystal growth in India, but we are working for that. We are basically buying this single crystalline silicon from China. So once a single crystal broke, and you will get the powder of it. But I think if we are using this polycrystalline silicon or amorphous silicon, definitely we will recycle that. Or from this single crystal, we can get the polycrystalline silicon. That we can do.
Yeah, at the moment actually it's the polycrystalline basically, which is basically being used. It's not the single crystal basically.
Okay, then if it is a polycrystalline, we can extract it and reuse it.
No, that's possible. I'm not telling that's not possible. What I am telling is basically that aspect has not got attention so far because see the development had taken place in last 10 years only. So and if you take the life of your solar module for say about 25 years, then means the recycling process will start basically sometimes in 2035. So that's why we have sufficient time at the moment to work on this. That's what the point basically which I am mentioning. That's possible. I'm not telling that.
Agree, sir. I agree, sir. Thank you very much. Because yeah, for their life, we will come for this problem. Sir, Manpreet, I will take one question. It is missed actually. Sarin Saju asked one question at YouTube. How can we increase the efficiency of the photovoltaic cells? This is the last question, sir.
Yeah, but see, the increasing the efficiency of photovoltaic cells. See, practically, if you look at how it has been working, see some of the slides basically which I have shown. Practically, what you require actually is whatever the solar radiation is falling on your cell, that should be absorbed basically practically. Now the lower wavelength basically is being absorbed at the top, and then the higher wavelength is going in the bottom, towards the bottom side where the bulk material is available. And practically at the junction level only, it's basically the charge separation takes place. So at the bulk, what happens basically the recombination, because it's not that in the P type the entire thing will be, means when the charge separation takes place, then it will be the holes only, and in the N type it will be the electrons only. You will have the holes, electron hole pair will be generated in both in the P side also. You will get the electron hole pair generated on the N side also. So ultimately, it's basically the transport characteristic basically of the material or the the recombination of this electron and holes pair basically. If you can reduce that process, particularly in the bulk area at the bottom side. So there are different methodology like the carbon nanotube and all those. From where basically you can bring those charge basically electrons or holes basically from it's practically not the hole basically, because hole hardly moves. It's basically the electrons basically to basically where the recombination means can become a free area at the near junction basically. That's how you can increase the efficiency. That's one way of doing the thing. The second is basically as in fact I could not complete that, and it was a good idea when we started sometimes in 80s in our laboratory in Nainital when we had been working in the luminescence. So practically in the solar cell, when the temperature increases, why the temperature increases? Because as the band gap, a limited particular wavelength basically, which is being used, or the means the band gap corresponding to that energy, that is practically used. So the higher energy basically your electron goes on the higher and then comes to your that conduction band. So that heat is generated. So how to reduce that? So your lower wavelength, if you can using the luminescence method from converting means transferring your lower energy to the higher wavelength side, which is corresponding to your band gap, then your this heating process can be reduced. So we worked actually started, but of course, as happens here, you do not get continued support, and ultimately the groups also disintegrate. It's not the continuous support. We stopped the work there in 1984 itself. Of course, I got the job, so I left that work. But in MIT, they continued that process and patented that technology in 2008. So what I mean to say is the efficiency can be increased if you can means the thermodynamic process basically, if you can reduce it some way, if you can use a better means some coat a dye over it, so that maximum absorption takes place and it gives you the wavelength corresponding to your energy gap. So you can increase the efficiency. So there are different methodologies which are, and that's how actually you have gone from 4 to now 21 and 24, and then you are also thinking to have multiple bands basically which could be used in the thing so that you can increase the efficiency. So that's how it happens. Yeah.
Thank you, sir. So if there is no questions, then we will close the session. Thank you, sir. Thank you very much for your valuable time and enlighten us with your knowledgeable talk. And sir, we wish to see you in person sometime at NIT Jalandhar. So please visit our organization as soon as the things will get normal. So once again, from behalf of the Department of Physics and the organizing committee of this course, I would like to thank you again for sparing some time from your busy schedule, sir. Thank you, sir. Thank you very much.
Thank you. Thanks a lot.
Tricky. Yeah.
Okay. One of my friend is working in Department of Physics, Devraj. So
Devraj is quite younger to us.
quite younger.
Yeah.
I think 4 year back, I think.
Yeah, he joined around 4 years back. Yes, he's my office neighbor. Yeah, next. We have a same next to my office. Yeah.
Okay. And Venu is also there. He is working on multifaric.
When mother when cryogenic.
Yeah, okay. He's in cryogenics.
Yeah, when he is in cryogenic. Yeah.
So they are working on multifarics. So we have a close association because I am also working on multifarics.
Yeah, I used to work on multiferroids way back for my PhD, but not anymore. Yeah.
Yeah. Now it is saturated. So actually, Manju told me that you know Professor R.K. Singh because I also have the association with Professor R.K. Singh at Bhopal.
Okay.
Yeah. So it's nicer to have your talk here. So just now I saw your email actually for the program. I have not seen that.
That's okay. I checked it out. I just checked it out, and then I found out it's a 1.5 hour talk.
Okay.
And so, what's the audience? How many people will be there? And
Okay. At present, the number is less because they will join at 3 o'clock. On an average, we have 100 people every day on this Microsoft team and around 100 at YouTube. But more than 1100 participants has registered for this course.
Okay.
So we have 30 participants overseas also from different country: Canada, France, Spain, Egypt, Nigeria, Philippines, Pakistan. So they are watching our this short-term course on YouTube, and some faculty members are watching this video in the evening because of their online schedule. Sometimes they may not
Yeah.
able to attend it.
Yeah, I can guess. I can guess that would be the case. So I would most probably I would be keeping it on a more like a tutorial kind of level, and rather than going, I have things which are quite detailed, but the graph I would then let it be more. If people want it to be more detailed, I'll explain. Otherwise, more like a tutorial kind of things would be helpful, I guess.
Yeah, that will be good, sir, because we have the mixed audience, we have the students from MTech. So if you cover the details, they will, uh, okay, that will help them to decide their project in futures. And people who want to start to work in the field of supercapacitor, they can also get benefit out of your talk.
Yeah.
And we will start the session within 3 minutes. If you want to share your screen, if you want to check.
Yeah, I will just share my presentation. You can have a look, and if it works, everything goes well, we should be ready to go. I
Yeah,
have
it's
just
working
shared.
well. It's working well. We can see your presentation.
Yeah,
Yeah,
very good.
everything fine.
Very good. So I would be using some pen paper here itself so that people can actually uh, also see what I am talking about. And if there's some answers to be given, I will be given here. So you
Yeah,
want me to keep the video on, or you want me to keep the video switched off?
it's sir up to you. I will switch off my video, and if you want to keep your video on, no problem for us. It's purely up to you.
Yeah, then let's do one thing. Let's switch off the video so that people actually pay more attention on the screen rather than trying to
Exactly,
watch.
exactly. So you keep your video on till we start the session. So I will invite our student who will take over the session in 2 minutes. So it's working well. So what about the students? I heard. So you allow the student to come in the institute?
Not yet. We have still not allowed the students to come back, and so hopefully we will start calling them next month or so.
Okay.
So not but yeah, because in any way in Bengal, the puja vacations.
Okay.
It's only for nearly 2 weeks. It's most of the things are bit relaxed. So it only picks up by, let's say it will pick up by first week of November. So the plan seems to be like that. We will get the students well. How about you?
Here also some PhD students are here, but BTech and MTech students not yet.
Okay. So yeah.
Hopefully we will have this all PhD students, or maybe MTech final year student or BTech final year student in coming month. But still, we don't know exact plan.
Okay. I hope we will have at least more than 4 people listening to this, because it can be the last talk and people may not attend.
No, there are many people. You will see at least, okay, right now 30 people, 25 attendees, and many organizers, and you and many other students. And people are watching at YouTube also. So you will have good audience. So it's good course.
No, I does not.
Yeah. So thank you, sir. Thank you very much for accepting our request to deliver talk on this short notice actually. So we are really grateful to have your presence here, sir. So now I would request Sarabjot to please take the session forward. Sarabjot, please.
Good afternoon, sir. Sir, I'm Neetu. I will take this session. Shall I start, sir?
Yes, Neetu, please.
Okay, sir. A cheerful afternoon to one and all present here. I need to welcome you all to the last session of the last day of this ESTC on advanced energy materials. Although the last one, I am sure the zeal to learn and make the earth a better place to live is ever so high. For this session, we are delighted to welcome another enigmatic material physicist, Dr. Amrish Chandra, Professor, Department of Physics, IIT Kharagpur. Dr. Chandra earned his PhD from Banaras Hindu University, Varanasi in 2004, followed by postdoc from Max Planck Institute for Polymer Research, Germany in 2006. He served as research officer in University of Surrey, UK from 2007 to 9 and then joined IIT Kharagpur. With over 67 journal publications, 65 conference papers, 4 books, and 1 patent as feather in his research cap, his area of interest include hierarchical nanostructures of metal oxides for energy applications, supercapacitors, gas sensors, and catalysis. He has undertaken numerous research projects funded by DST India, MPG Germany, Indo-UK Eukaryote Thematic Exchange Project, Max Planck Society Germany, DAE, BRNS, BAG India, and the like. With 11 years of teaching experience, he has supervised about 15 PhD students and many MSc MTech students. He has strong collaboration with many foreign research groups from UK, Germany, Australia, and France. He is a humble recipient of Young Scientist Award thrice from International Conference on Electroactive Polymers 2004, Indian Science Congress Association 2004, and Department of Atomic Energy India 2010. Max Planck India Fellowship Award by Max Planck Society Germany in 2010 and Endeavour Executive Fellowship Award by Government of Australia in 2018 clearly portrays his diligence and dedication to discover new paths of success. With due respect, I request Dr. Amrish Chandra to enlighten us all with his talk on supercapacitor.
Okay, Neetu, thank you very much for this introduction. And I don't know whether I do deserve it to be introduced in this manner. Can you see the screen?
Yes, sir.
Okay, very good. So, good afternoon, everyone. I am Amrish Chandra, as Neetu just introduced. Let me just switch off the video so that it becomes, I am mostly, yeah. So, as Neetu said, I am presently working at IIT Kharagpur, and I have been associated with this institute and been working here from the year 2009. And today, on the request, rather than I would say on the order of Dr. Singh, I would like to share some of my recent research activities which my team at IIT KGP is undertaking. And hopefully by the end of this talk in approximately an hour and a half, you would have some idea towards the direction in which we are moving and the next generation supercapacitors, which are continuously attracting quite a bit of research activity. Because as I was told that the audience is from MSc students, MTechs, and faculty colleagues, I'm saying this topic is still attracting significant research activities. Significant not only in terms of the number of publications which are being published in various journals, significant also because new phenomena, new physics, new chemistry, and more so, new applications for these devices are still being reported on daily basis. So it is not a routine kind of work which is just finding more papers with similar outcomes. It is new kind of work with new kind of applications, and therefore the future still holds a lot of promise to work in the field of supercapacitors. Some of the topics which I would just focus today would be our work on hollow nanostructures. What do I mean by these terms will be explained as we go along. And if you have at any point you feel you would like to discuss or you need some clarifications, you're free to just raise your hand and click and we can have a discussion. So before I start, it is absolutely essential that uh, I acknowledge the real workers, the team who has been working with me. These are the people who have directly worked for their PhDs or MSc or 1 year MTech or 1 year MSc projects, at least with me in my team. And they are the people who have actually allowed me to become the spokesperson of the work which we claim is coming out from IIT Kharagpur in the field of supercapacitors. So these are my students, and they are quite well placed all over the world. And the next theme which I would share, which is another thing which is essential, is to acknowledge the funding which has been obtained from various funding agencies. The funding is also essential to carry out high-end research. It's not about that if you have more funding, you will get better papers. It's about supporting your research team with basic equipments and the requirement of chemicals, the basic characterization tools. So the funding which has been obtained are from various agencies from India as well as abroad, and they are of the tune of around 3.5 crores. And therefore, we have been able to make a reasonably well-established research facility in the field of supercapacitors at IIT Kharagpur. Our current interests lie in the field of metal oxides nanostructures, and the applications of these structures lie from supercapacitors to lithium-ion batteries. And the one which I would not be touching today also include catalysis or water splitting. So I would not be touching on the bottom two, but hopefully we would get enough time to talk about supercapacitors in today's talk. As I said, we would like to focus on the energy storage technologies. During the course of last 3 days, you may have heard about people talking about the need for storage, the intermittent nature of renewable energy systems, which force the energy landscape to include a dedicated energy storage component. I would focus primarily on electrical energy storage. And these storage technologies are completely new, crucial elements of this new energy landscape based on renewables. And for the electrical energy storage, there are two major components which are sectors which are driving the current interest. One comes in from network or grids. Grid can be off grid, or it can be grid or And the second component is your transport sector. Along with that, if you look around, the third component which is there is now the mobile technologies. Now, these mobile technologies are not only the handies which you use to make phone calls or your smartphones. These mobile technologies involve your laptops, your smartphones, your wearable electronics, and it is a multi-trillion economy as of today. And along with the top two, which were considered as conventional, the use of electrical energy storage in mobile technology is driving the research activity in energy storage devices and will continue to attract both fundamental and applied research activities in many more years to come as we go towards miniaturization or we go towards flexible systems or we go to higher energy density systems. And as we go along, you will find many more applications which will come in. So these are the three primary driving forces which are attracting interest in energy storage devices. So if you see what happens in a conventional grid, the power generation and the distribution infrastructure. So in a conventional power generation grid, the power generation and distribution infrastructure actually is based on a low error margin. You don't, there is no, it's a very low error margin grid. So it's a very stable system. You don't expect a lot of variations in the grid supplies. And it tries to bring in near instantaneous balance between the supply and demand. So as the demand increases, it immediately tries to build or generate more electricity, pump it into the grid, and tries to counter the requirement for demand. So there is a continuous effort to bring in an instantaneous balance. And this balance is actually, for the grid applications, you will find there are thousands of turbines which are running all around. So if the demand is very high, then more number of turbines are brought online. And if the demand falls, the number of turbines which are contributing towards the electricity generation and then their subsequent transmission are reduced. So this is the way the present system works as of today. But if you investigate, you will find most of these turbines stay ideal for the majority of time. So you will find that because there is a drop in demand, the turbines are taken out of the network and therefore they are lying ideally and they are not contributing. And this leads to the loss in the generation capacity for the whole network. This means if I can continuously use this generation unit, and if I am able to combine it with proper storage capacity, so generation plus storage will give me an efficient system. So, till few decades ago, this component was ignored. But not now. In most of the present generation units, which also include the renewable energy systems, the storage technologies have become an integral component for the whole network. And the best way to have these electrical storage systems working at high efficiencies is to convert chemical energy into electrical energy, because they share the same vector, that is the electron. That is why you find that people say, yes, you have a battery, a next generation battery, or lithium ion battery, or an aluminum cell battery, or a fuel cell. They are using the term electrochemical or chemical energy storage systems. This is because they share the same vector, that is electron. And moving from, so playing with the electron for the in both the systems become straightforward, and therefore you can have electrochemical devices such as fuel cell, supercapacitors, or batteries. Fuel cell, it basically works on the reverse principle of electrolysis of water. That is, the electricity is produced by the oxidation of hydrogen which is while coupling another phenomena, that is reduction at the second electrode, and the end product is water. Whereas supercapacitors are based on the capacitive properties of double electron layer at the electrolyte interface. Just remember this term. We will be discussing quite a bit on this term, the electrolyte electrode interface or electrolyte interface. And why the term supercapacitor? We have been conventionally, or from our school days, have been hearing the word capacitors. So if you look into the typical values for capacitance, the typical values for conventional capacitors were of the order of micro to few milli or maybe millifarads. This was conventional capacitors. But supercapacitors are, the word super was added in front of the word capacitor because they can give millions of times greater capacitance value than typical capacitors. So in comparison to capacitors, in this case, the values can be hundreds farads per gram. Whereas conventionally, it was milli. Here you can go to hundreds of farads. And it is expressed in terms of farads per gram, that is per unit mass, or farads per centimeter cube in terms of per unit area. More, I will discuss it further. Whereas in batteries, how do you differentiate a battery from capacitor? Here, they store electrical energy by the reversible redox reactions that occur at the in the constituent materials that are used to fabricate an electrode. So there is a slight difference between batteries and capacitors. So a non-technical difference between batteries and supercapacitors. What is it? Both seem to be working very, very nicely, and they have similar response characteristics. So a supercapacitor is basically a high powered device. That means it can deliver large power in short period of time, whereas a battery is like a marathon runner or a person who is walking in a 20-kilometer Olympic race, where it has nearly constant power, but for a long period of time interval. So this is, the batteries are high energy density, whereas supercapacitors are high power densities. So they give large power in short period of time, whereas batteries give large energy for significant amount of time. So this is a non-technical differential. So very quickly, let's revise. What is the need of chemical and electrical energy storage? They are used also for load leveling. So if you generate more power, the demand is less, you can store that energy, and vice versa. If the demand suddenly shoots up and you already have stored energy, you can pump in that stored energy into the grid or supply to the end user and counter the requirement of the peak load. So these are the things which we have to keep in mind. Supercapacitors, they can provide stronger on-demand burst of voltage. That means high power, short period of time, and they can charge extremely quickly. They have few hundred thousand, that means few lakhs of cycle life, and they don't rely on chemicals, making them a slightly better environmental friendly system in comparison to batteries, which actually have much shorter, lower number of cycle lives. If you charge them or overcharge them, they can get damaged. They are expensive. And if you start charging them at very fast rates, try to compete with the charging rate of supercapacitors, they may end up getting damaged. So if you draw a Ragon plot, that means you have drawn the power density versus the specific energy curve. Then this is called a Ragon plot. You will see where these systems actually. So let us start our basic discussion on supercapacitors. What are they all about? So supercapacitors are made up of two electrodes, you see, negative electrode, a positive electrode, and electrolyte, and a separator. A separator is an ion conducting separator. That means it does not allow electron to go through. That means that because of the role of this separator is primarily to avoid any, so this separator avoids short circuit. So it avoids short circuit. So the two electrodes cannot come together and you don't have any electrical short circuit because of that. This junction is called your electrolyte interface. And this is where the whole physics lies for supercapacitors. What is happening at the electrolyte interface? So if you look into the electrode interface, you have, let's say, a positively charged surface. Then you have the negative charge followed by the solvated ion deposition. So this layer is called the Stern layer, and from the outer Helmholtz layer, so you have two layers, the inner Helmholtz layer and the outer Helmholtz plane. From the outer Helmholtz plane, in the bulk of the electrolyte, there is a small gradient before the system reaches back to a neutral state, and that is called your diffuse layer. Where is the origin of the specific capacitance? Let us try to investigate in few of these slides. So you will see supercapacitors, as we saw. You have electrolyte interface, and they are classified as electric double layer capacitors or pseudo capacitors. And the ones which show both these response characteristics, then you can call them as hybrid capacitors. So EDLC, the electric double layer capacitors, store energy non-faradically. That means there is no electrochemical or the exchange of ions taking place. Whereas for pseudocapacitors, you have redox reactions taking place. And in hybrid capacitors, you have, these are all nano-sized structures. They have certain porosity, therefore you are seeing some gap in the middle. This is an extremely representative way of explaining this structure. So you need to pay attention, because it's not like exactness, but just an attempt to make the understanding easier. Then you have a separator. So these gaps are not there, but they are just used to show that they allow the ions to cross, but electrons are not allowed. So you have electrolyte. When you charge it, the ions move towards the opposite charges, and you have the formation of the ions near the electrode surfaces, and then they form the two layers. So positive, negative, positive layers. You charge it, you have these solvated ions also reaching the surfaces. The electrons are received by the electrode, and then they are allowed to move out from the surface. So that is a typical way of explaining a supercapacitor. And there are various models which have been used to explain the supercapacitive system. It is so initially it was the Helmholtz model where it introduced that there was a sudden change in the uh, so it was a well-defined layer of the at the electrolyte interface, electrode-electrolyte interface, which was formed. The Guy-Chapman model said no, it was not like a layer which was getting formed. They said there was a continuous decrease from this interface towards the bulk, and there was a continuous decrease in the gradient. Whereas the Stern model came in, and then they said it is a combination of both. You have the Helmholtz layer where you have the deposition in a manner where you find a parallel plate capacitive type behavior. Along with that, you have a gradual decrease of the charge, and it takes certain region before you reach the normal neutral state of the electrolyte. So it's a combination of three, and you for all the three models, you can write the mathematics, and you would find that basically your total capacitance, that is 1 by C, equals to 1 by CH and 1 by CD. That means in the diffused region and in the Helmholtz region. And the way you use in experimentally, how do you calculate? There are two measurement techniques which are used. One is your cyclic voltammetric technique, and the other is the charge discharge profile. In most of the places you don't really see how do we actually get the formulas. So it is very simple in both the cases. We start with the definition of capacitance, and if you are working with changing scan rates, then you define dq in terms of IDT, and if you divide your CS by M, you get the specific capacitance. So capacitance is coming in as a function of scan rate S. You integrate over the starting potential to the final potential. And if you divide by the mass, you get the specific capacitance. Similarly, if you are measuring the charge discharge curve, so if you are measuring from charge discharge curves, whereas in the previous case, you were measuring as the CV curves, so you can actually use the similar mathematics and then write the same capacitance in terms of the current by the mass, and you will find how much time it takes to charge, and you measure the capacitance in the discharge cycle, not in the charging cycle, because what is useful to you is the energy it delivers, not the energy it actually takes in to, or energy which you pumped in. Suppose the capacitance is only working at 50% efficiency, then what is useful to you is only the 50% value of the specific capacitance which you may have calculated during the charging cycle. Therefore, for supercapacitors, you should report the values you get in the discharge cycle and not the charging cycle. And similarly, you have the energy densities, which is given by half CV square. This is similar to the capacitance, which you wrote, the energy density which you wrote for capacitors. So if you want high energy densities, then either you increase the specific capacitance value or you increase the voltage value. But for the aqueous solutions, which are based on water, because of the water dissociates at approximately 1.2 volts, the limiting values are 1.2 volts. There are ways where people have actually found out to increase this working potential by changing the work function, but that we will see later if we get operate at approximately 1.1 volt or so that you don't lead to the dissociation of the energy. So the only way to have very high energy densities are coming in by increasing the capacity of the material. And the devices which are reported, this is a laboratory. I'm not talking about the pouch cell or the cylindrical cells which can be, or the typical capacitor designs which are used. When you're working in the lab, you use these CR 2032 specifications, which primarily means that it's a coin cell which has a width of 20 millimeters and the thickness is approximately 3.2. And how is it made? You have the cap. At the bottom, you have the enclosure, so you have the two cap. Then you make a film which includes your positive electrode. Over that, you put a separate, then a negative electrode. Then you have a spring before you put a spacer so that there is no short circuit taking place, and you can drop enough electrolyte so that the device does not actually goes dry. And then you compress it in a coin crimper, and then you crimp it to form the shape of a CR2032 configuration. This is the typical cell design, and then you clip it, you put wires, and then you can do the measurements. That is the typical way of doing the measurements. So the main factors which control the performance will immediately become clear. They are the electrode materials and the electrolyte. And I'll try to show that in addition to these, you can also have external factors which can significantly change the performance of supercapacitors. They can be magnetic field, pressure, frequency, that means vibrations, external vibrations, or changing the temperature environment near the device. It's not the internal temperature I'm talking, which may change as a function of cycling. I'm talking that if you operate a material, a supercapacitor, let's say at room temperature, then you heat it at 35 degrees, then you make it to operate at 50 degrees, and then you may operate at 70 degrees, whether the performance will remain the same or will it show some changes, and if they show some changes, what can be the reasons? So this is what we like to see. As the workshop is primarily on materials, so let us try to focus on materials. You may have been introduced over the last 3 days on nanomaterials with different orders of confinement ranging from 1D, 2D, or 3-dimensional confinements. So you can have different order of confinement. This means as you change the confinement, you actually change the surface area. And as the surface area changes, the performance of the device changes. one should also be very clear that not all materials, it's not like that you can choose any random material and you can start working and expect a supercapacitive behavior being observed in the system you have tried to investigate. We have to find systems which will have a reasonable or high electrochemical performance. So, two types of systems are used. One are based on carbon and the others are based on transition metal oxides. These are used in pseudocapacitors, whereas if you have both the electrodes which are based on carbon, then they are mostly the EDLC type supercapacitors. And if you are using both the electrodes as if you have same electrode material, in both the electrodes, then you call it as symmetric capacitors or symmetric supercapacitors. And if you don't, that means one of the electrode has material A as the active material, whereas the counter electrode or sorry, the second electrode may actually be based on carbon, which is different from A, then you call it as an asymmetric cell. So that defines your symmetric or asymmetric configurations. So how do you, that is where the importance comes. You have to choose which, suppose I ask you a very simple question, which carbon electrode will you use? It is, you have hundreds of carbon structures which are available, which are readily investigated by many teams. So which one is useful to you? Then you must synthesize those materials. They can be purely carbon microstructures. They can be graphene oxide or reduced graphene oxides, or they can be graphene quantum dots, they can be graphene, they can be carbon paper, carbon sheets, carbon fibers, electrospun fibers of carbon. So the synthesis becomes extremely critical. So the synthesis becomes critical. You cannot ignore the synthesis protocols because they will define the reproducibility of the measurements, the reproducibility of the device performance characteristics, and therefore they will define whether the material which you are making can be produced in bulk. And if they can be produced in bulk, then only they become useful to the industry and will attract attention from the industry. If you make a material which can only be made once, but it may give you the best performance ever reported, but if it cannot get reproduced or it cannot be produced in bulk, then it will not attract the attention from the industry. So these are the typical carbon structures we are talking about. You can have various forms of activated carbon, or you can have carbon spheres, and you can have small carbon spheres, or you can have large carbon spheres. You can see from SEM or TM micrographs. You can have the graphene structures, you can have the graphene oxides, you can have the reduced graphene oxide, you can have a sheet-like structures or few layers of graphene or graphene oxide structures. You can have graphene quantum dots. So that means you are making carbon structures with three-dimensional confinement, that means you have all the three sides of the carbon with dimension less than 100 nanometers. How do you define a nanomaterial? A nanomaterial is a system which is made of particles which has at least one of its three dimensions in the range of 1 to 100 nanometers. And if you have a quantum dot, that means it has all the three dimensions which are in the range of 1 to 100 nanometers. Once I have made the materials, then you will perform the basic characterizations. The basic characterizations are what? X-ray diffraction. X-ray diffraction will tell you the stacking or the interplanar distances. You can use the Bragg's law, perform these scattering measurements, and you will find out the typical interplanar and intraplanar. If you have short range ordering, then you may actually talk about the system being more amorphous. But if you start getting some kind of a peaks, that means well-defined diffraction profiles, then you will say that you have the ordering which is in between short range or long range. If you have well-defined peaks throughout the diffraction profile, then you can talk about the long range ordering in the crystal lattice. And then you can find out the similar behavior, how the bonds which are formed between the atoms which are arranged in a lattice. So if I have carbon, then there are bonds. So you have nearest neighbor, 1 and 2 in this case for this. So how these bonds are vibrating, that means how the carbon atom is actually vibrating, and then how does it stabilize, you can find out using the techniques of infrared spectroscopy or Raman spectrum. As I said, the most important thing is in the field of electrochemical is your surface area values. So if I have a particle, what is the effective surface area which becomes available to store charge? If the surface area is small, then the number of sites which are available to me would be less in comparison to the surface area. So why is it important? Once again, why is it important to investigate different materials? You can see as you make different material, you play with the confinement, you change the surface area which are shown by those materials. Along with that, the pore radius, that means the porosity, how densely packed those systems are, or if there are porous, that means why it is important to have porous. If there are some porous materials, then the electrolyte ions can actually penetrate in and reach the inner surfaces of the electrode material and undergo the electrochemical performances. So along with your surface area, the second term which plays the role is the pore size or the pore radius, and the measurements which are performed or called the BT measurements, which is coming in from the three scientists which use these measurements, which are Brenner, Emmett, and Teller. The three scientists which discovered this absorption-desorption curves, and by analyzing the absorption-desorption curves, you can find out the nature of pores. You see they are different. The curves are the different. So you can have either type 4 type 2 type, or type 1 type structures. And using the measurements, or what you study as dynamic light scattering in your MSc, the dynamic light scattering measurements, you can find the particle size distribution. If the distribution is narrow, then that is considered to be a system which is more useful, because then that means you have large number of particles which have similar characteristics. So you would not like a broad distribution, but you would actually prefer a narrow particle size distribution. So as we said, advantages of nanomaterials: high surface to volume ratio, allows the transport length for both mass and charge transport, leads to high surface area. They have low density. That means they can return the same less number of less weight of material can actually deliver the similar performance. So that means you can reduce the size and the weight of the overall device. And if I can reduce the amount of material which is required, I hope that the cost can also be brought down. I said, I hope that the cost can also be brought down. Why? Because it is not always true, because the synthesis protocols can also lead to cost escalation. So the material may actually be extremely high performing, but there can be additional factors which can limit its use. And then we have the transition metal oxides, which are used in supercapacitors. And these are the conventional properties which make the transition metal oxides useful for electrochemical performance. And my team actually specializes in making large number of metal oxides in large number of morphologies. So you can see we can make a typical spherical particles to cactus-like, to rose-like, to kind of network-like structures. We can also make hollow structures. So you can see you have a cavity in the middle. So these kind of structures are called hollow structures. These are visible both using SCM or TM. So it's not like that they are only visible at very small sizes. They actually can stabilize in large sizes. So you can clearly see that there is a cavity in the middle. So you can make hollow structures, or you can make different kind of solid structures, or you can make various kind of layered structures, either stacked layer, single layer. Along with that, you can also see, if you see this figure, there are some like perforations. So these are typical porous structures. So they are not neither they are solid nor are they hollow, but they have perforated mesh-like structures on the surfaces. These are called porous structures. So and we can make large number of materials in our group. And it is believed that the next generation systems will be using the hollow structures much more than your solid structures. So you will not be using the solid structures, but actually you will be utilizing the hollow structures. And why? If you see this schematic, nanomaterials, you have the interaction only at the surface. If you believe that all the nanomaterials, when they are forming, they actually do not agglomerate. That means this is only the case when they are not agglomerating. But in the reality, what happens the moment you bring the nanoparticles which are formed during a synthesis process, they agglomerate. So they are agglomerating. So the effective surface area which you were believing for this material, this whole surface area, then this one, all the area becomes available is not the case. Effectively, you are losing all the areas which are at the boundaries which are coming in from the agglomeration. So you lose a lot of areas and the interactions are much more. So solid structure have this problem. So if I use hollow structures, that means I have a cavity which allows open structure from inside as well as you have from outside. So you can double the surface where the interaction will take place. And if that is the case, both will start contributing, and in that case, the overall performance should nearly double if it is an ideal case. But at least we can claim for till now that there should be some increase. And when we started work, it was not so easy, but over the last 6-7 years, we have now been able to attain where a level of confidence where we say, yes, we can make hollow structures easily, and they always supersede the performance of solid structures. So if I draw this schematic and put it in supercapacitors, so you have solid structure based surface electrode and a hollow structure based electrode. You use the electrolyte. When you charge these solid structures, you see you have the solvated ions entering the porous structure comprising of solid materials, particle, and then they undergo an electrochemical performance. But if I try to perform the similar experiment, there will be interactions inside as well as outside. So the overall performance will increase. And now there are large number of techniques which are available for the synthesis of hollow structures. They can include soft template. They can also be template free, or they can be hard template. Today we will just try to see with some results which we have been obtaining using the soft template route of making hollow structures. Let us take one of the most common materials, the copper 2 oxides, or copper based nanomaterial for supercapacitors. So, as I said, now whatever we have talked, let us see if we can put them into perspective. First thing important is synthesis. Okay, if that is the case, I will synthesize the material using various routes. That means I will change the synthesis conditions. If I am changing the synthesis conditions, is there any change in the morphology of the particles which are forming? So if I follow the different protocols, then I can see in one case I get structures with cavity in the middle. In the second case, I get particles with a small cap on their head. Whereas in the third case, I get particles which are homogeneously distributed throughout the bulk, but they more so show porous or more nearly solid sphere-like morphology. So I have three types of particles already. And that is why you should types of particles. And that is why you should pay a lot of attention to the synthesis of the materials. Because if you change the slightest of conditions, here you see I have just doubled the amount of dextrose in comparison to what was used in the case of obtaining octahedral type solid copper oxide, you may actually end up getting hollow structures. So that is why it is absolutely essential to maintain similar synthesis conditions when you are talking about the reproducibility of results. So are they actually copper oxide? Yes, you again perform the diffraction measurements. You find that they can be easily refined using the space group of copper oxide. They have a similar diffraction profile, only the width changes, which tells me that the size of the particle is actually changing, and there is no appearance or disappearance of any peak, be it being diffraction profile, be it in the FTIR data or in the Raman spectrum. So your vibrational modes are remaining the same. That means the nature of the bonds which are forming between copper and oxides are remaining the same. The nature of vibrations are remaining the same, and the crystal structure is remaining the same. So it's not like a phase transition is taking place and therefore the performance is changing. It is not because of the phase transition which is leading to the change in the performance. So this is, now we have these types of materials in us. Next thing what we had discussed, find out the surface area. And immediately you will see that in the case of hollow structures, you have values which are, let's say, approximately 10 meters square per gram. For porous, it is 13 meters per gram, and for solid, it is 4 meters square per gram. So it is clear that from solid to hollow, it is more than 2 times the surface area. Similarly, you can get zeta potential, which shows that the effective charge concentration of the surface is also changing. So let us see whether the electrochemical performance of these hollow structures are improving or they are remaining same, and what are the typical values. What measurements did we talk about? We had talked about the CV measurement. So current versus voltage measurement. So as a function of scan rate. So you have as a function of scan rate, how fast you go from 0 to the maximum voltage or the voltage window in which you are working from initial to final, and how fast you scan the overall variation, and you perform these measurements continuously. This is what is being talked about. You perform with different electrolytes because you expect the performance to change with electrolytes. So you have material as well as electrolyte, which you are changing and try to find out which electrolyte gives the best performance. So it is clear that you have the KOH and giving you the highest specific capacitance. Then you perform the next round of measurements, that is the CD measurement, the charge discharge, the voltage from initial to final, and the time it takes to reach the maximum, and then discharge. So you find out from the discharge cycle, you find out the time it takes, and using the formula which you had I had discussed earlier, you can give the values and you will get the specific capacitance. And you can clearly see that the specific capacitance is changed. This is for copper oxide, solid, and showing an octahedral shape. Similarly, you perform the measurement for porous structure. And finally, you perform the same measurement for hollow structures. So you make the material, you then make the electrode, then you make the basic characterizations, and then you do the electrochemical performance. And that is not straightforward. Every needs time, and every result has to be understood before you can proceed to the next step. Because if you don't optimize your operating voltage window, your system will not give the desired output. Suppose you are using an aqueous electrolyte and you start putting a voltage of 2 volts, then you will not see anything, and you will see the device crashes after a few cycles, and you have absolutely no idea why it happens. The reason is because the electrolyte is dissociated. If your system can actually work in 1 volt voltage window, but you operate it in 0.5 volts, then your overall energy density comes down. Now the third factor, suppose your material is such that it works in the negative side of the potential, then if you apply from 0 to plus 9 volts, you will not get plus 0.9 volts, then you will not get the desired result. So every step you have to optimize. So you have to optimize the operating voltage, you have to optimize the scan rate, you have to optimize the electrolyte. Then only you will get certain values which you can claim to be millions of times higher than the conventional capacitors. So if I put the values in perspective, you can clearly see that the values obtained by the hollow structures are, so if this is approximately, let's say 80 farads per gram for solid structures, then for the hollow structures, you are somewhere around 160 or so. So you can clearly see similar measurements you can find from the charge discharge curves. You will always find that the best performance is coming in from the hollow structures, and the reasons for that should be clear to you, that because it provides more number of active sites, therefore they have higher performance, and but as the crystal structure is remaining the same for all the 3 particles, they are maintaining the valence state. You still have copper 2 oxide, it has not transformed to copper oxide. Therefore, their cycling life, it remains this, or this Coulombic efficiency remains the same. That if you operate it for, let's say, a large number of cycles, in this case we have operated for 300 times, 3000 times, then the voltage, the initial capacitance to the value after 3000 cycles, the values are similar. So as long as you are more than 90%, then for the field of supercapacitors, you consider it to be an acceptable cycling stability. So till now, it should be clear that hollow nanostructures could serve as novel electrode materials for supercapacitors. The next thing is electrolytes. So similar to what we did for electrodes, you can investigate large, so the whole gamut of work still remains incomplete. You have hollow structures of various shapes. It can be spherical, they can be rod-like, they can be cone-like, they can be big. So till date, mostly metal oxides, hollow structures which are spherical or slightly deformed sphere type of structures, they are at the most the pillar-like structures are being investigated and reported. But hollow structures of other morphologies remain unexplored. So there is a large scope of work which remains to be completed. So next thing is redox electrolytes. So what happens? What are redox electrolytes? They are basically the supporting agents which provide extra redox ions to undergo redox activities at the electrode electrolyte interface. In this case, let me just, so if you have large and more number of ions which are going to take part in the interaction, the redox activities, the overall specific capacitance should increase. And these redox additives do not alter the performance of your host electrolyte up to an optimum concentration. If you go on adding redox additively uninhibited, that means you don't optimize the concentration, then beyond a certain concentration, you will find that the system will start showing some peculiar response characteristics because the nature of the electrolyte itself starts to get significantly modified. So you have to optimize the addition. It's not like that you can add 10x millimolar. You have to actually optimize the concentration. So once you have added the electrolyte, you perform the similar type of measurements, and you will see during the optimization, you will find that it is up to a certain value, let's say 75 millimolar of potassium iodide, and similarly for potassium ferricyanide, you have the shape of the profiles do not change, and you have the capacitive behavior. Still, you have the capacitive behavior. So, what you can do now? I have changed the electron, and so I have already obtained nearly 100% improvement in comparison to the solid structures. And now I support these already high performing supercapacitors with an optimum concentration of electrolyte modified by redox additives. If this is the case, then the overall specific capacitance should increase significantly. And if this is true, then you are into business, because then you can reduce the cost, you can reduce the weight, while bringing nearly 100% improvement or enhancement in the specific capacitance value. And this is what we have shown, that you use, let's say, potassium iodide, you can go from solid structure was what? Approximately 80 farads per gram. This was for solid. But from solid, you can actually go to 306 farads per gram. That is nearly 4 times higher. And what have we done? We have used a very logical step that is, increase the surface area, performance will increase. Improve the redox activity at the electrolyte interface. How do I improve the redox activity? I provide higher number of redox active species. That is, in this case, by using a redox additive modified electrolyte. And once I do that, can I get a very high performing supercapacitors? And this is true. This is true and logical. So once I have made the device, the next way of making it useful for industry is people only actually perform the measurements and then they report at room temperature. But in reality, it is no more the advantageous or useful activity which will be there. Why? If you use a capacitor in your mobile technologies, and today if I am sitting in a part of a country which sees significant variations as a function of weather, then today the temperature may be around 10 degrees, and in summers it may actually go to around 50 degrees. So my storage system itself will see a variation of 40 degrees. So will the performance remain same, or will it change as a function of temperature which is in the vicinity of the device? And if so, then what is the magnitude of change? So what do? Now you perform the similar measurements. These are not straight away measurements, so you have to be careful. They are non-trivial exercise. So you make the system, and then what you do is to perform the measurements at different temperatures. So let's say room temperature, then you heat it at 45 degrees, then you heat it at 65 degrees, and after it comes back to room temperature, you make the performance once again. So you heat it, and when it cools back, you must measure the performance once again. And in this case, you can clearly see this is room temperature measurement, this is the room temperature measurement. But the nature of curves are slightly different. This means that the temperature cycling is also playing appreciable role in modifying the response characteristics in supercapacitors. So you must also perform the measurements at various temperatures. In this case, we actually saw increased specific capacitance values. And the reason for this can be because when you heat the material, the lattice actually expands, and due to the expansion in the lattice, you may see that the pores, the channels which are allowing the intercalation and deintercalation of the electrolyte or the solvated ions are actually opening up. And if the channels open further, then you will see that the specific capacitance will go up because more interactions will take place. So this happens in all kind of materials, be it be solid, be it be porous, or be it be hollow. So the increment in specific capacitance at a current density of 1 ampere per gram. So when you go from room temperature to 65 degrees, you actually see that for a particular redox additive also modified system, for solid structure, there was an increase of 13%. Then for porous, it showed 22% enhancement, whereas the hollow structures showed an enhancement of 32%. It is the similar trend in unmodified systems also. That means you have pure potassium hydroxide there also the performance is similar. The next aspect which I will try to cover in next 5 minutes is people have always been talking about supercapacitors as a function of voltage. And then they have been making these systems using magnetic ion-based electrodes, such oxides like iron oxide, manganese oxide, cobalt oxides, and then, but they always ignored the effect of magnetic field in them. They said, in this, it's only the charge which is collecting at the electrolyte interface, and that is the only thing which should be taken into consideration while calculating the specific capacitors, and this is the model which have been used. Then we asked a simple question last year, of nearly 2 years back, is like, in the field of supercapacitors, there is a question which remains ignored, that is, if the device performance is investigated near magnetic field, will the device that has been formed using magnetic electrode materials get affected or not? And the abstract just finish with this sentence that the answer is yes. It actually does and is affected significantly. So then we made all kind of oxides using different magnetic ions and performed the magnetic measurements. So you can clearly see, let's say if you see at 30 Gauss, 50 Gauss, 100 Gauss. So you made a device, put it in the field between the poles of a magnet, electromagnet, change the magnetic field, and perform the same measurement. Simple. No nonsense. So as a function of changing magnetic field, you can clearly see that the area under the discharge curve actually changes. The area is increasing significantly, and if the area is increasing, that clearly shows that the specific capacitance is increasing, and it actually, for let's say for iron oxide, if the value at 0 Gauss was, let's say, 90 farads per gram, then it could actually go up to 140 farads per gram when you applied 50 Gauss. So there was a increase of nearly 50 to 60% in the specific capacitance value. And the answer lies in the additional force which is felt by the electrolyte ion, the force which is originating from the Lorentz component, that is Q dot. Initially, you only investigate Q dot E, but when you apply a magnetic field, then you have an additional component, that is Q dot E plus Q dot V cross B term, which increases the force which is felt by the electrolyte ions, and therefore you have a more channeled movement of ions towards the electrode, and if that happens, then you increase the overall interactions, and you have the significant increase in the specific capacitance values. So you see increase. And this is true in all magnetic ions. And finally, let me end up by asking a very simple question, that will it be true that if I make a material which has a very fashionable morphology, gives me the best specific capacitance, will it be useful, or there is an additional thing which should be considered? And if you're interested, you can read this paper where we have answered that the highest surface area and specific capacitance cannot be the only deciding factor, because when you involve materials which have the best performance, you have the best performance, you have the best outputs, but because they may end up having a more involved synthesis route. So if you perform the life cycle assessment studies, that means you take care of all the input energy which are there during the formation of the raw material or the reactions or the filtrations, then you may find that the overall carbon footprint of the best performing material may actually be very, very high, and it cannot be used. And this is what we have shown for cobalt oxide, that even if you have the best performing material, which is a sheet-like structure, it cannot be used because the carbon footprint, which is like 53 kgs, in comparison to the lowest specific capacitance measurement, which only has the performance, let's say, of output of 23 kgs carbon dioxide equivalent, then you have to also investigate the carbon footprint of each and every material before you can sell it to the industry or convince the user that I am not increasing the carbon footprint by using a green technology. Then it will not be a green technology. So if you want to sell a supercapacitor as a green energy storage technology, you will also have to perform the life cycle assessment studies of these devices before they become useful for any other application. And with this, my time is up, and I would probably stop presenting, and then I will go back and open the discussion for the talk for discussion. Thank you very much.
Thank you, Professor Chandra, for a nice illuminating talk, and it is really useful for all of us. So now this session is open for discussion. I request the participants who are joining us on this Microsoft team, they can ask the question by raising their hand. They can unmute themselves and ask the question directly, and then we will take the question from our viewer at YouTube channel. So, question please.
Hello.
Yes.
Good afternoon, sir.
Good afternoon.
Sir, can we use the combination of supercapacitor in EV without battery?
In electrical vehicles?
Yes, sir.
Yes. Electrical vehicles is the massive application region for supercapacitors, because during the regenerative braking, when you are using regenerative braking, you are generating energy. You actually store this energy from capacitor and then only transfer to your main storage system, or when you are accelerating the system where you need a burst of energy, then it is not extracted from the battery, you actually provide this burst of energy from the capacitor. It does not come out from the battery, so that the battery remains safe, which is the most expensive component of your overall energy storage system, integrated system, and therefore you take this burst of energy from the capacitor, which is slowly charging itself from the energy from the battery. So it does not, you don't take the energy out of the battery.
Good afternoon, sir. Myself, Dr. I.D.
Yeah.
Sharma is speaking. I want
Yeah.
to know that instead of copper oxide, we can utilize MnO2, aluminum oxide, etc.
Oh yes,
for a supercapacitor.
that is what I said. I showed the large number of materials which we have synthesized, and we use maybe 50 different combination or maybe 100 materials. So you can use any of these. So I just to make the understanding easier, so I just took a simple example which people have heard, but you can use any transition metal oxide combination which you use. And most, other than copper oxide, manganese oxide is one of the most common ones which have been used. And so you can use it. The similar performance have also been reported there also. We have also done that.
For example, aluminum oxide and Na2O.
Yeah, you can. We have investigated, but it depends on whether which electrolyte combinations will you use, what will be your operating voltage window. So everything will have to be optimized once again, and then you can perform the
Okay,
device.
thank you, sir. Thank you, sir.
Any other question, please?
Hello.
Yeah.
Sir, hello, sir. Can we use supercapacitor where we can charge and discharge simultaneously, and we can replace the battery?
This is a very interesting question. Whether you would like to discharge at the same time, then you don't have a system which is defined out. But yes, we can. There are. We call, if you look into our paper, we call these systems which are called as super bats. We call them as super bats, which have a characteristics of supercapacitors as well as of batteries, and they have been fabricated using electrode materials, which are so a supercapacitive electrode material as well as a battery material, and the performance is such that they show not only high power densities, but they also have a high energy densities. So yes, and we call these kind of systems as super bats. Some people call them as hybrid systems, but yes, most of the work nowadays is actually moving in this direction, because you would, at the end of the day, what you like, battery which can charge fast will also have, that means you want to increase the power densities of the battery. If you go from supercapacitor field, you actually want systems which have higher densities. So I can store for long period of time, large amount of energies, have large cycle life, but then discharge as not very fast, but as per the requirement of the device. So both actually would like to converge at one point, and that is where the Ragon plot is saying that you are looking at hybrid systems which have both high energy densities as well as power densities.
So actually in the last slide that you showed, so you told about carbon footprint and all, right? You told you should check the carbon footprint before confirming. So can you show the slide again? So what was the configuration of the first, this thing? Like you had the last one was a solid for cobalt oxide, last was solid, second one was sheet, and the first one was?
Disc.
So what is the diameter of the disc? Like if you compare the disc and the sheet also has a sheet is also thin.
Yes.
And
yes.
So
yeah, so disc and
not the diameter, sir. I meant the thickness. The thickness of the disc. The thickness of the disc and the sheet. If you compare, like
yeah.
So.
Yeah. What happens?
The disc also is thin, right?
Yeah, that is correct. What is happening is when you make the sheet-like structures, they are the highest performance cobalt oxide what we obtain. But the sheet-like structures also had a porosity which was much higher than that obtained in disc lines. So they were also a two-dimensional like a structure, but they were like solid structures. Whereas the sheet-like structures, they had some gaps, so they had some porosity, and therefore their performances were very much higher. But they were of the carbon footprint also went
Carbon
up.
footprint, because sir, carbon footprint of disk was the lowest. That was very low.
Yeah,
in
that
the
was
table.
low. But the performance, because the solid structures, they were solid structures, so they were not able to return the specific capacitance as per the requirement.
Okay. So, sir, in that, when you explain the comparison between like the solid and why we go for a whole, I mean, why we prefer a hollow structure to a solid structure. So, when you showed that figure, you told like how, like, when see in case of a solid, you told that the what is it, the interaction occurs because the solid is porous, and in case of a hollow surface, it can interact both inside and outside the surface. So in case of a solid structure, also can't it interact on the outside of the surface, the particles?
Yeah, in the case of solid structures, you will have interactions mostly at the top surface. But if you go into slightly more detail, if you see the schematic which I showed, it was also that the agglomeration of these solid structures, they are actually killing the active surface area which becomes available to us. So although the surface area may be much large, but if I look into two phases, the active surface area which is at the interface, but now suppose if I make a cavity here, then even if there is an agglomeration here, the cavity still remains active for me to perform. So during the agglomeration process, the effective surface area which was getting killed in solid structures remains active in the case of hollow structures. That is what we anticipate.
Okay, thank you, sir. Thank you, sir. Thank you, sir.
Welcome. If you have any other queries, you can drop me an email or that's not a problem.
Okay, sir. Thank you, sir.
Any other question, please?
Hello.
Yes.
Hello. Sir, I have one question. Why supercapacitor doesn't work with AC current?
It's a simple capacitive behavior you're talking about. You are not talking about, so you are stabilizing an electrolyte interface where you have defined the reference electrode, the outer electrode as the electrical electrode. So therefore you will have a DC current where you will find the double layer which is getting formed, and then only you will find the DC component forming the electrolyte, the charge layers.
Sir, what happens if we apply AC current in supercapacitor?
So you will have, it's just like you want to go from AC current and then you are continuously changing the polarity. If you continuously change the polarity, then you are unable to stabilize the interface. You don't have the formation of the interface. So you are continuously changing the polarity of the sides, and then you don't have the double layer getting formed. So you have a continuous flow.
Okay, sir. Thank you, sir.
Professor Chandra, I want to ask question in continuation of this question. Because I am a purely a dielectric guy, so for supercapacitor, I saw that is there any role of this loss, tangent delta? I have not seen any curve related to the loss, which is mostly we used to present when we talk about a capacitor. So is it not useful in case of supercapacitor?
What you are talking about is tan delta. So tan delta, when you measure the dielectric constant, then you measure the tan delta value, and then you calculate the imaginary part of the dielectric constant. This is what you do in the loss component. Okay, so you have the real part, the C into tan delta, so epsilon prime into tan delta gives you epsilon double prime, and that constitutes your loss factors. The loss factors in this cases are straight away not in terms of your dielectric losses. They are there, but then you see them as IR drop. So what you see is when you see the dielectric curve, it should be ideally a triangular curve. What you see is shape going up, then there is a small dip, and then it comes. So the losses which are there at the IR, they contribute into various. It can be a change in the dielectric behavior. Then you can have the change in the internal resistances, and then These are your internal resistance drop, which are taking care of the dielectric constant based loss, which you're talking about, that is tan delta. So that these components are there in the IR losses at the top of the CD curve. What you are talking about is most probably is the epsilon double prime, which is obtained from the loss factor that you apply electric field, and how well the electric field is actually thrown out is, and if you have losses, you don't you have tan losses coming in, that is given as tan delta. So these are slightly different aspects, but the dielectric losses and other losses included in the system are coming in at the IR drop, the internal resistance drop.
So in a simple way, if I want to say that if we are investigating the supercapacitor, we have to simply just measure the IV curves and see that, okay, whether they are following the same path or not during increasing the voltage and decreasing the voltage. Am I right?
More so, yes. If you have, but it is not straight as simple as that. You have to have, you should be working in the voltage window where the redox activity actually takes place. You cannot apply more voltage than that, otherwise you will have overpotentials and you will have the system breaking down. So it is the operating voltage window which has to be defined, and in the operating voltage window you can cycle it n number of times. This is what you will say simply.
Sir, one more last question from my side. You have shown the IV curves at different temperatures. So as you increase the temperature, there is variation in the IV curves and there is some formation of some peaks. So
yes,
do such peaks has any role, some specific significance?
And so if you see in the CD curve, there are some specific peaks which appear. That means these are the additional redox activities which become prominent at in this temperature range. So they are the redox peaks which are there, and the redox species become active in that temperature range. So that can happen because the surface area, the surface becomes more activated, and therefore it is able to underperform some more redox activities, and therefore you are seeing some appearance of the peak. So these are basically associated with the redox activity, which is being performed by the electrode at different temperatures. So this is the redox activity.
Thank you, sir. Thank you very much, sir. So Neetu, please take some question from YouTube. We have some question at YouTube. Neetu, are you there?
If there are any other questions, which then people can also send an email, and I will be happy to answer them personally also. No problem.
Okay, Professor Chandra, I will read if Neetu is not available there. So Mr. Hemant Kumar Jaswal, he asked the question for problem associated with supercapacitor. If we use them in automobile, I think it's already mentioned. Automobile with the help of grid, I think it's already answered. Then Dr. Pradeep Chandra asked the question, can supercapacitor be used to store electricity under open circuit condition and used as and when and where required like battery?
No, not like that, because the self-discharge is very, very high. The self-discharge of supercapacitors are very high, so not like in open circuit, it's not used.
Okay.
Unless you make some stacks of supercapacitors and you make large stacks where some of the companies are actually selling. So if you go, they are using some big stacks of supercapacitors, and then they can be using. But the conventional ones, the ones which we are talking about, they have a very, very fast self-discharge, very high self-discharge. So it is not recommended.
He asked another question, that whether we can use supercapacitor in Delhi Metro. If yes, then how?
Yeah, so I also answered the same question. These are the systems which are used during the regenerative braking. So they are placed in between. The use of capacitors in locomotives were there initially. If you use diesel-based locomotives not in there. So during the ignition, you spend a lot of diesel. So many countries and many locomotive industries have actually used this concept of using the ignition for the purpose of ignition and passing charge so that the diesel can you can start the diesel engine is actually from the energy supplied from supercapacitor. This is one. And the second is the regenerative braking. So when you are braking the systems, then you can store certain energy and then you can deliver it to the battery so that it can act as a safety fuse between your battery and your source. So because these are much cheaper than your battery, so it can also act as the safety fuse, which similar to the way conventional capacitors are used, that they are used as safety component between your main motherboard and the input supply. So you can use them. And during regenerative braking, so for if you are having systems to convert it, then you can always store the energy. Yes.
Thank you very much. So this is the last question from Tejas. How surface to volume ratio of nanomaterials and hollow structure enhanced efficiency of supercapacitor?
Okay, surface to volume ratio. So if you have smaller surface, lower volume, then that means the particles are much smaller. So you have much smaller particles, though active surface is much higher. So more a system active surface is available for performing the redox activity. That means you are not going to lose a lot of material which is in the bulk of the system, which is in the bulk and is not coming in the surface. So your surface to volume ratio, the volume is much smaller. You have most of the particles on the surface and they become actively available for performing the redox activities. Now, in addition, but you still have some bulk. So if you have this surface area, along with that, if you open the cavity in the middle, then the top surface is already taking contributions and giving contributions similar to expected from a conventional nanomaterial. Along with that, you have opened another surface area. So if you increase the active overall active surface area, you will increase the overall redox activity. And that is why it is expected that the hollow structures will improve. And this is not only true for supercapacitors. This has been shown by us in catalysis, that the hollow structures have much higher capacities. You can also use these materials with the one cavity in EMI shielding. You can also use them in batteries. So these have already been shown. If you would like to see some papers, you can have discussion with me and with the library. I will ask my library if the rules permit, we will be able to send you the papers.
Okay, so if there is no more questions, so before that, I want to request to the participant, if you have any question, you can write to me or you can directly write to Professor Chandra, and I'm sure that he will definitely answer your question.
Yeah, I will be more than happy. Yes.
Yeah. So, sir, we are really grateful to you that you spare some time and agreed to deliver the lecture on this course on a very short time, sir. Very short notice.
Pleasure.
So, thank you so much, sir. On behalf of the Department of Physics at NIT Jalandhar and organizing committee, we are really very much thankful to you, sir. And we will be happy to see you at NIT Jalandhar in person as soon as the things will get normal. So we are ready to welcome you here, sir. Thank you, sir.
Thank you very much. Thank you very much. Okay, bye.
Bye, sir. Okay, so dear participants, we are moving forward for our valedictory function. So it is really a great pleasure for all of us to interact with all of you during this 5-day session. It's really very encouraging to answer the question of the participants and I hope you all also enjoyed this event. So now I request co-coordinator Dr. Abhinav, coordinator of this course, Abhinav Pratap Singh, to formally thank all of you on this occasion. Abhinav sir.
Yeah, hi everyone. So
Or
before we say,
hello.
Yes sir, yes.
Maybe we will have Harlin ma'am opinion before that, and then you conclude.
I think we should take some opinion of the participants also. If they want to say anything about the course, if they want to give any kind of feedback that where we could have improved, like what was the good part, what could have been improved. We know that there was initial some problem regarding Google Meet, and we tried to fix it with using Microsoft Teams. Please, everyone is welcome if they want to say anything regarding the experts, the quality of the experts that we have called, the topics, the relevance of the topics, and all those things. Please, you are welcome. If anyone has to share anything, please go ahead.
Myself, Dr. I.D. Sharma from CCR PG College, Muzaffarnagar.
Yeah.
Really, your team invited speakers are greatly has a depth of knowledge, and they have planned presentation and utilizing a simple and ordinary life examples. So we salute with heart all of the speakers and all the organizing team. Thank you. Thank you so much, sir.
Okay, thank you. Thank you so much, sir. So, any other, if someone wants to share anything?
Hello.
Yeah, we can hear you. Please continue.
Sir, in your upcoming session, if you mention any solar photovoltaic cell about in this webinar, then it is okay, sir, for us. In any renewable sources of energy or any renewable sources, how that solar energy is useful in the upcoming days in the industries like Thermax, like ECHEC or any nuclear power plants, how this is useful, it is okay for me, sir.
Yeah, okay. We have got your suggestion. Yeah, thank you. Thank you for that. Yeah. Anyone else? Yeah, okay. I think, Kiran sir, if there are no other questions, so maybe we can have some words from.
Hello?
Yeah, please continue. Yeah.
I am audible, sir?
Hello, my name is Sneha. I'm an electrical engineer, and actually this course was very, very nice. Okay, kudos to the team at NIT Jalandhar for having organized it so well. It was a very good course all the days. I mean, the speakers, the way it was presented, and it was arranged in a very good manner. Keep it up, everybody. Very good work. Keep it up.
Thank you. Thank you so much, ma'am.
Hello?
Yeah, we can
audible,
hear you.
Sir?
Please. Yeah, you are audible. Please.
Actually, very good afternoon, sir. Kiran, sir.
Yes, good afternoon.
Actually, really, it is a very fantastic, I think, short-term course. Really, very wonderful. I must say congratulations to your team. Actually, we all people are learn many things. Actually, the course attended another one, I think, last week before in your department. I think this is very scientific short-term course. And it's necessary nowadays because the energy is very important topic nowadays. We need it in future. In coming 20, 30 years, we will face a lot of problem about energy. So you give one kind of boost to all of us to know many things, how to minimize future. we not many things in.
Yeah, thank you so much, sir. Kiran sir, shall we take some now? Shall we begin with taking some words from?
If someone want to say quickly, one or two, very quickly. So we are already delayed in our session. I think, okay, we will have the words from our head of the department. So Harleen ma'am.
Hello.
Good evening, sir. Good evening.
Tahir, yes.
Yes, good afternoon or evening. I can say I'm all the way from Nigeria. I am a faculty member from one of the universities there. I really appreciate your effort, and the course was very nice and interesting. I use all the time I have for me to attend this course because it is very important. And I have learned a lot, and I gained a lot of areas where researches can be made. And also I have developed an interest in some of the presentations made by eminent presenters. So thank you very much, and I really appreciate your effort, and I hope this kind of courses will be organized in the near future again. Thank you.
Thank you so much.
Yes, now I request our head of the department, Dr. Harleen Daya, to say a few words about this course. Harleen ma'am, please.
Okay. So good evening, everyone. So I really feel honored to thank all the speakers, including Professor Rohan Srivastava, Professor Manju, Ranjan, Ranjit, Professor Vishwas, Professor Sundareshan, Professor Ogle, Professor Mitra, Professor Pant, and Professor Chandra. I am so thankful to the speakers for accepting our invitation and agreeing to deliver the talk. And I'm sure the young listeners might have gained a lot from their presentations. So at the same time, I also feel very proud to see the perfection of my colleagues, Dr. Mehra, Dr. Kiran, and Dr. Abhinav, and all the PhD students who have been working very hard for organizing the course. So they have taken care of all the logistics, and I congratulate you all for the event and would encourage you to organize more such events, because I see the feedback of the participants is so good that they want you to organize more such courses. So wish you all the best and congratulations once again. Thank you.
Thank you, ma'am. Thank you very much. So now I would like to request Dr. Abhinav Pratap Singh, coordinator of this course, to present a formal vote of thanks. Abhinav sir, please.
Thank you, Kiran sir. As you know that we are the coordinators, we have just coordinated. You wanted to listen, we provided the experts. So I would like to thank the experts who have covered the various aspects of the energy materials. And I hope that the talks has been very, very useful for you. We have tried to do our best in arranging the experts. We are thankful to the participants as well, because their enthusiastic response, not only from within the country but outside the country as well, has been fantastic, and it motivates us to organize more such courses. We would like to thank the director, Dr. L.K. Awasthi. We would like to thank Dr. Harleen Daya, head of the department, all our faculty members, staff members, research scholars, and all the students who have helped us organize this course. As I have said previously also, that it is always a pleasure to work with Dr. Rohit Mehra and Dr. Kiran Singh. They are very hardworking, and it reflects in the quality of courses that we are offering. So I wanted to keep it very short because you have been listening for the talks for a long time. So that is it from my side. It is bye from NIT Jalandhar, and I hope to see you all again online and hopefully in person as well. Thank you, everyone.
Thank you, Abhinav sir. So there are a few announcements before closing the session. So today I will send you the feedback link, and there will be another feedback form which will be related to your certificates. So please fill it properly. There should not be any mistake in your name or emails. So we will send you your certificates very soon. Thank you very much for your cooperation and interest in this course. So now we want to say bye bye. Thank you very much and hope to see you sometime in person or some online courses. So we will close the session. Thank you very much to all the participants. And yes, please.
Sir, can we get the recorded sessions of this?
See, you have the video. You have the YouTube link with you, so you can download the video at your end by yourself.
Means in that video also YouTube, sir, we are not getting the PPTs clearly, sir. That's why I'm asking, sir.
Okay, Mane Kaushik, there is a problem only in one talk. For other talk, there is no problem. So it is absolutely fine. And we don't have other recording. Otherwise, we can share you, but I don't have any other recording other than this.
Kiran sir, may I just add one thing, that if we were recording all these sessions, those recording will automatically appear in your Microsoft account. So you don't have to worry about it. But as Kiran sir has said, we have not recorded anything, and whatever things are there, they are available on YouTube. Yeah.
Okay. So once again, I want to thank all the faculty member of Department of Physics, NIT Jalandhar, all the research scholars, and especially our Physical Society team. Yes. Somebody want to say something?
Professor Kiran sir.
Yes, Naresh, please say. You were saying something.
Feedback from second page is not opening, sir.
Okay, your voice is not clear to us. So you can, whatever the question you have, please send me the email. I will respond you. I will respond back definitely. Okay. So now, last but not the least, I want to thank all our research scholars, Physical Society team, Physical Science Society team for their constant support to organize this event. And thank you everyone. Hope to see you sometime at NIT Jalandhar or other online courses. Thank you very much. So we will close the session. Bye bye from NIT Jalandhar.
Thank you everyone. Bye bye. Thank you.
Bye.
Main feedback from second page is not opening, sir.